There is a monster at the center of our galaxy, 4 million times the mass of the Sun, invisible, inescapable, and so dense that if you replaced our Sun with it tomorrow, the event horizon would fit comfortably inside the orbit of Mercury. Its name is Sagittarius A star, and it has been sitting there 26,000 light-years away, quietly warping the fabric of reality since long before Earth existed. We know it's there because we can see stars whipping around it at thousands of kilometers per second, tracing orbits that only make sense if something unimaginably massive is holding them in place. But here's the part that should unsettle you. We have never actually seen a black hole, not directly. What we call seeing is just watching things fall toward them, observing light bend around them, measuring the screams of matter as it crosses a boundary from which nothing, not even information, can return. The event horizon is not a place, it is a border in space-time where the rules stop working, where up and down lose all meaning, where your body would be stretched into a strand of atoms so thin that scientists had to invent a word for it: spaghettification. And if you somehow survived that, if you crossed the horizon intact and looked back toward Earth, you would see the entire future history of the universe play out in seconds, while back home, your fall would appear frozen in time forever. This is not speculation. This is what Einstein's equations predict. This is what happens when gravity becomes so extreme that it bends not just space, but time itself. And what waits at the center, beneath all that warped geometry, is something our physics cannot describe. A point where density becomes infinite and the mathematics we trust simply give up. So what actually happens inside a black hole? And why do the answers force us to rethink everything we thought we knew about reality? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. A star is dying. Not slowly, not gracefully, but in the most violent way the universe knows how to end anything. The core runs out of fuel. For millions of years, nuclear fusion has been holding the star up, pushing outward against gravity's relentless squeeze. Now that push stops, gravity wins. And what happens next happens fast. The core collapses. In less than a second, a sphere of matter larger than Earth crushes down to a point smaller than a city. The outer layers, still falling inward at a quarter of the speed of light, hit that rigid core and bounce. The rebound sends a shockwave tearing back through the star, ripping it apart from the inside out. The explosion that follows, a supernova, shines brighter than an entire galaxy for weeks. The blast scatters gas and dust across light years. Everything the star ever made, carbon, oxygen, iron, silicon, all of it flung into space. And at the center, where the core used to be, something new remains, something that breaks the rules. If the collapsing core weighs more than about 3 times the mass of our Sun, nothing can stop it. Not atomic forces, not neutron degeneracy pressure, not any known law of matter. The collapse continues past every breaking point physics has ever identified. The core compresses beyond the density of a neutron star, beyond anything that can be called solid or liquid or gas, and keeps going. It falls through itself. Gravity pulls it inward until the mass becomes so concentrated in such a small space that the escape velocity at its surface exceeds the speed of light. And when that happens, you no longer have an object, you have a black hole. This is not a metaphor, it is geometry made real. Space itself warps so severely around the collapsed core that it folds inward like a trapdoor. Anything that crosses a certain invisible boundary, the event horizon, cannot climb back out. Not because some force is holding it down, but because every direction that used to point away now points toward the center. Outside becomes a concept that ceases to apply. Stellar black holes form this way all the time. Astronomers estimate there are somewhere between 10 million and 1 billion of them scattered throughout the Milky Way alone. Most of them are invisible. They do not glow. They do not pulse. If a black hole is not actively feeding on nearby gas or locked in orbit with a companion star, it is just a knot of curved space drifting silently through the galaxy, impossible to see and almost impossible to detect. We know they exist because occasionally we catch one in the act of eating, or we spot the X-rays from gas spiraling into oblivion, or we detect the gravitational waves from two black holes colliding billions of light-years away and merging into something even heavier. The smallest known black hole in the observational record weighs about 3.8 times the mass of the Sun. It is paired with a companion star, which is the only reason we found it. The black hole pulls gas off its partner. The gas heats up as it falls inward. That heat produces X-rays. We saw the X-rays and worked backward. Most stellar black holes are larger than that, typically somewhere between 5 and 10 solar masses. But gravitational wave detectors have picked up signals from collisions involving black holes weighing as much as 100 times the Sun, formed not from single stars, but from the violent merger of smaller black holes in dense star clusters where collisions are common. The process that makes a stellar black hole is well understood. A massive star collapses, the core implodes. If the remaining mass is heavy enough, a black hole forms. Simple, violent, repeatable. This is the bottom tier of the black hole hierarchy, the smallest, most common type, the kind the universe manufactures in bulk every time a massive star reaches the end of its life. Then there is the top tier. And the top tier makes no sense. At the centers of galaxies, including our own, sit black holes weighing millions or billions of times the mass of the Sun. These are the supermassive black holes. They are not rare, they are everywhere. Almost every large galaxy ever surveyed contains one, sitting at the core like a gravitational anchor. The Milky Way has one, Andromeda has one. Distant galaxies spotted by the James Webb Space Telescope when the universe was less than 1 billion years old already had them. Fully formed, massive, active, and nobody can tell you how they got that big. Stellar black holes grow by eating. They pull in gas. They collide with other black holes. Given enough time and enough material, you could, in theory, grow a stellar mass black hole into something much heavier. But the math does not work. The timeline is too short. The most distant, supermassive black holes we have observed existed when the universe was less than 700 million years old. That is not enough time to grow a black hole from 10 solar masses to 10 billion solar masses by normal feeding. Even if the black hole ate constantly at the fastest rate physics allows, called the Eddington limit, it could only double its mass every few tens of millions of years. Start with a 10 solar mass seed, feed it non-stop for 700 million years. You end up with something thousands of times heavier than the Sun, maybe tens of thousands if conditions are perfect, not billions. So where did the supermassive black holes come from? One possibility is that they started big. If a massive cloud of primordial gas in the early universe skipped the normal star formation process and collapsed directly into a black hole, it could form a seed weighing tens of thousands or even hundreds of thousands of solar masses right from the start. That head start buys time. grow from 100,000 solar masses instead of 10, and the timeline begins to close. Some simulations suggest this kind of direct collapse could happen in the chaotic environments of the first galaxies, where gas was hotter and metal poor and more prone to runaway collapse. The problem is, we have never seen it happen. It remains a hypothesis, a way to make the numbers fit, not a confirmed process. Another possibility is runaway mergers. In the dense cores of early galaxies, stars collided, black holes formed. Those black holes collided with each other. Each merger kicked the growing monster into a higher weight class. Repeat the cycle fast enough, in a small enough region, and you could build something enormous in relatively little time. The trouble with this idea is that it requires an extraordinary amount of luck. Mergers are messy. When black holes collide, they lose energy to gravitational waves and get kicked out of their host systems. You need just the right conditions, repeated over and over, in a very small volume of space for hundreds of millions of years. Possible, but not easy. A third idea, one that some researchers have started taking seriously, involves primordial black holes formed in the first fractions of a second after the Big Bang. In the earliest moments of the universe, tiny fluctuations in density could have collapsed directly into black holes without ever becoming stars. If those primordial seeds existed, and if they were heavy enough, they could have started growing before the first stars even ignited. In that version of the story, supermassive black holes were never built, they were born. The honest answer is, we do not know which explanation is correct. We may never know. What is clear from the data is that the early universe was building things faster than our models say it should have been able to. Supermassive black holes are the hard evidence. Their existence forces us to admit that something about the timeline, or the physics, or the initial conditions of the universe is not what we thought. Between the stellar mass black holes and the supermassive ones sits a gap, the missing middle. Intermediate mass black holes, if they exist, should weigh somewhere between 100 and 100,000 times the mass of the Sun. They would form in dense star clusters, or from the merger of smaller black holes, or possibly from the collapse of very massive stars that only existed in the early universe. Astronomers have been searching for them for decades. The evidence is frustratingly sparse. A handful of candidates have been proposed based on X-ray emissions from globular clusters or gravitational wave signals that suggest colliding objects heavier than stellar mass but lighter than supermassive. None of them are confirmed beyond doubt. The intermediate mass category remains the least populated and least understood tier of the black hole family. Nobody is sure if they are rare because they are hard to make, or if they are just hard to find. What we do know is that black holes come in a range of sizes, and that range spans more than 10 orders of magnitude, from 3 solar masses to 66 billion. That upper number comes from an object called TON 618, a quasar sitting more than 10 billion light-years away. It is the most massive black hole ever observed, and it should not have existed when it did. The light we see from TON 618 left when the universe was less than 4 billion years old. By the time that light began its journey, the black hole already weighed 66 billion times the mass of our Sun. The timeline problem appears again, louder this time. You cannot build something that heavy that fast unless the rules changed, or unless the starting conditions were radically different from what we assumed. Black holes do not behave the way most people think they do. They do not suck. They do not reach across space and pull things toward them like vacuum cleaners. Gravity works the same for a black hole as it does for any other massive object. If you replaced the Sun with a black hole of exactly the same mass, The planets would not spiral inward. Earth's orbit would stay the same. We would freeze to death in the dark, yes, but gravitationally speaking, nothing would change. A black hole only becomes dangerous when you get close to it. Close enough that the curvature of space becomes extreme. Close enough that tidal forces, the difference in gravitational pull between your head and your feet, start to stretch you. Close enough that time itself begins to behave strangely. All black holes spin. This is not speculation. Angular momentum from the collapsing star gets conserved during the formation process, and because the core shrinks to such a small size, the rotation rate skyrockets. The fastest known black hole spins more than 1,000 times per second. At that speed, the event horizon is not a perfect sphere. It bulges at the equator. Space itself is dragged around the black hole in a process called frame dragging, creating a region where nothing, not even light standing still, can avoid being pulled in the direction of the spin. Stand too close to a spinning black hole, and the universe starts rotating around you, whether you move or not. The nearest known black hole to Earth is called Gaia BH1. It sits about 1,500 light-years away, paired with a sun-like star in a binary system. 1,500 light-years is close by galactic standards. If you drew a map of our stellar neighborhood and marked every confirmed black hole within a few thousand light-years, the map would be almost empty. Not because black holes are rare, but because the ones that are not actively feeding are invisible. They do not emit light. They do not announce themselves. They drift through the galaxy like ghosts, detectable only when something falls into them or when their gravity bends the light of a more distant object in a way we can measure from Earth. Most of the black holes in the Milky Way will never be found. They are too small, too quiet, too far from anything that might reveal their presence. They are holes in space, waiting in the dark. Some of them are drifting through regions where no stars will ever pass close enough to be consumed. Others are orbiting the galaxy in long, lonely paths that will never bring them near anything interesting. A few are headed, very slowly, toward the galactic center, where they will eventually be absorbed by something much larger. That something larger has a name. It weighs 4 million times the mass of the Sun. It sits 26,000 light-years from where you are sitting right now, and it has been there, silent and patient, for as long as the Milky Way has existed. We cannot see it directly. We have never photographed it. But we know it is there because the stars nearest to it move in ways that nothing else could explain. They whip around an invisible point at speeds that should not be possible unless something extraordinarily massive and extraordinarily compact is holding them in orbit. We cannot see it. That needs to be said first, because everything that follows depends on understanding that single uncomfortable fact. The supermassive black hole at the center of our galaxy, the object holding the Milky Way together like a gravitational anchor, has never been directly observed. Not with visible light, not with infrared, not with anything that behaves the way normal astronomy expects objects to behave. It does not glow, it does not reflect, it does not announce its presence by doing anything a telescope can point at and photograph, and yet we know it is there. We know its mass down to a precision that would make most measurements in physics jealous. We know where it sits, we know how fast it spins. We have watched stars whip around it at speeds that should not be possible unless something extraordinarily massive and extraordinarily compact is sitting exactly where we cannot see anything at all. The object has a name, Sagittarius A star. Astronomers write it as Skr A star, and they pronounce it Sagittarius A star, not Sagittarius A asterisk, though the symbol looks like one. The name comes from its location. If you point a radio telescope toward the constellation Sagittarius, toward the dense band of stars marking the direction of the galactic center, and you listen carefully to the radio noise coming from that region, you will detect a bright, compact source of synchrotron radiation. That source is Sagittarius A star. It sits almost exactly at the gravitational center of the Milky Way, roughly 26,000 light-years from Earth. For context, the farthest human-made object, Voyager 1, has traveled about 23 light-hours in 47 years. It would take Voyager roughly 470 million years to cover 26,000 light-years if it were headed in that direction, which it is not. Sagittarius A star weighs 4.297 million times the mass of our Sun, give or take about 12,000 solar masses. That is not an estimate, that is a measurement, the product of decades of painstaking observation and orbital mechanics. The precision comes from tracking stars, not distant galaxies, not gas clouds. Individual stars orbiting the galactic center so tightly and so fast that their motion can only be explained by something invisible sitting at the exact point they are circling. One of those stars, a blue giant called S2, completes a full orbit around Sagittarius A star in just under 16 years. Its closest approach brings it within about 17 light-hours of the black hole, roughly 4 times the distance from the Sun to Neptune. At that point in its orbit, S2 is moving at nearly 3% the speed of light. That is almost 9,000 kilometers per second for a star. No object moves that fast unless something extraordinarily massive is pulling it. Run the math backward from S2's orbit, plug in Kepler's laws, and the mass of the unseen object falls out cleanly. 4.3 million suns, confined to a region smaller than the orbit of Mercury. There is only one thing in physics that can pack that much mass into that little space: a black hole. Not a neutron star, not a dense cluster of smaller objects, a black hole. The tightest orbits observed around Sagittarius A star rule out every other possibility. If the central object were a cluster of stars or stellar remnants, the individual components would have radii large enough that the orbiting stars would collide with them. They do not. If it were a ball of dark matter, it would have to be impossibly dense and stable in ways dark matter does not behave. The only option left on the table is a supermassive black hole. And once you accept that, everything else about the galactic center starts to make sense. Astronomers did not set out to find a black hole. They were mapping stars. In the 1990s, 2 independent teams, one led by Reinhard Genzel in Germany and the other by Andrea Ghez in the United States, began using adaptive optics and infrared cameras to track individual stars near the galactic center. Infrared was necessary because visible light from that region gets absorbed by clouds of dust scattered along the 26,000 light-year line of sight. Infrared cuts through the dust. What both teams found was a cluster of stars moving in tight elliptical orbits around an empty point. Not a dim point, not a faint point, an empty point. No star, no visible object, just curved trajectories wrapping around nothing. Year after year, the stars moved. The observations piled up, the orbits closed. By the early 2000s, the case was airtight. Something with the mass of 4 million suns was sitting at the center of the Milky Way, and it was not emitting any light. Genzel and Ghez shared the 2020 Nobel Prize in Physics for that work, along with Roger Penrose, who proved mathematically that black holes are an inevitable consequence of general relativity. The event horizon of Sagittarius A star, the boundary inside which nothing can escape, has a radius of roughly 12 million kilometers, That sounds enormous until you remember that the Sun, which weighs 4 million times less, has a radius of about 700,000 kilometers. Shrink the Sun down to the density required to make it a black hole, and its event horizon would be about 3 kilometers across. Scale that up by 4 million, and you get 12 million kilometers. The size scales linearly with mass for black holes. Double the mass, double the radius. The event horizon is not a physical surface, it is a mathematical boundary in curved space. Cross it, and every direction you could move, including backward, now points toward the center. The geometry of space itself has folded inward like a trapdoor. You have not hit a wall. You have stepped off a cliff that has no bottom and no sides and no way back up. If you were somehow standing at a safe distance from Sagittarius A star, say a few hundred astronomical units out where the tidal forces would not immediately kill you, the black hole would not look like much. It would not glow, it would not shimmer. You would see a perfectly circular region of absolute blackness, slightly larger than the event horizon because of gravitational lensing, surrounded by a faint halo of light from gas and dust orbiting nearby. That halo would be dim. Sagittarius A star is not an active feeder. It is not a quasar. It is not pouring radiation into space at galaxy-scale luminosities. Most of the time, it just sits there, quiet and patient, occasionally swallowing a stray cloud of gas or a star that wandered too close. When it does feed, the accretion process generates X-rays, which we can detect from Earth. Those X-ray flares happen irregularly, lasting anywhere from a few hours to a few days. Between flares, the black hole is almost invisible. The only reason we know it is there is because of what it does to everything around it. That brings us to the image. In May 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. Not a photograph of the black hole itself, which is impossible because black holes do not emit light, but an image of the glowing ring of gas orbiting just outside the event horizon. The ring appears because photons emitted by hot gas on the far side of the black hole get bent around the event horizon by the extreme curvature of space, creating a bright loop that outlines the shadow of the black hole itself. The shadow is larger than the event horizon by a factor of about 2.6 because of the way light behaves near the photon sphere, a region where photons can orbit the black hole in unstable circular paths before either falling in or escaping. The image confirmed what decades of orbital mechanics had already told us. The central object in the Milky Way is a supermassive black hole. The shadow size matched the predictions. The brightness distribution matched simulations. Everything lined up. The Event Horizon Telescope is not a single instrument. It is a network of radio telescopes scattered across the planet, synchronized to observe the same target at the same time. By combining their signals using a technique called very long baseline interferometry, the array acts like a single telescope the size of the Earth. That scale is necessary because Sagittarius A star, despite its enormous mass, appears incredibly small in the sky. The angular size of its event horizon as seen from Earth is about 50 microarcseconds. That is the angle subtended by a tennis ball on the surface of the Moon. No single telescope on Earth can resolve details that small, but an Earth-sized array can. Barely. The 2022 image was the result of years of observation, data processing, and computational modeling. The raw data alone filled several petabytes of hard drives, which had to be physically flown to a central processing facility because there is no internet connection fast enough to transfer that much information. The final image, a blurry orange ring on a black background, does not look impressive at first glance. It is one of the most important pictures ever taken. Sagittarius A is calm by supermassive black hole standards. For comparison, the black hole at the center of the galaxy Messier 87, which the Event Horizon Telescope imaged in 2019, weighs about 6.5 billion solar masses and is actively feeding. It powers a jet of plasma that extends for thousands of light years, glowing brightly across the electromagnetic spectrum. Sagittarius A does not do that. It does not have jets. It does not blaze in X-rays. It is mostly dormant, waking up only occasionally to consume whatever drifts too close. Astronomers estimate that the accretion rate, the amount of mass falling into the black hole per year, is extraordinarily low. Most of the gas in the galactic center is too hot and moving too fast to settle into a stable accretion disk. It just swirls around the black hole in chaotic orbits, radiating energy and drifting away. Only a tiny fraction actually falls in. If Sagittarius A were feeding at the rate typical of an active galactic nucleus, the Milky Way would be classified as a Seyfert galaxy, and the radiation from the galactic center would be bright enough to affect star formation across the entire disk. It is not. The black hole is there. It is massive. It is just not hungry. That calm nature might be temporary. There is evidence that Sagittarius A was more active in the past. Astronomers have detected enormous bubbles of gamma-ray emission extending tens of thousands of light years above and below the galactic center, structures called the Fermi bubbles, after the space telescope that discovered them. The bubbles are thought to be remnants of a massive outburst from the central black hole, possibly triggered by a large accretion event a few million years ago. If that interpretation is correct, then Sagittarius A is capable of much more dramatic behavior than what we see today. It just happens to be in a quiet phase. How long that phase lasts is anyone's guess. Black holes do not operate on human timescales. A million-year pause between meals is nothing. One of the stranger things about Sagittarius A is how little we actually feel its presence. You would think a 4 million solar mass object sitting at the center of the galaxy would have a noticeable gravitational influence on the solar system. It does not. At 26,000 light-years away, the pull from Sagittarius A on Earth is negligible. The Sun's gravity dominates locally. The black hole does hold the galaxy together in a broad sense, anchoring the orbits of billions of stars, but its direct influence drops off with distance. The orbital speed of the Sun around the galactic center is about 230 kilometers per second. That speed is determined not just by the central black hole, but by the combined mass of all the stars, gas and dark matter between us and the center. If you removed Sagittarius A entirely, the Sun's orbit would barely change. The structure of the galaxy depends more on the distributed mass of everything in it than on the single massive object at the middle. The black hole is important, yes, but it is not running the show the way a lot of popular descriptions suggest. The stars closest to Sagittarius A live in an environment unlike anything else in the galaxy. The nearest cluster, called the S-stars, orbits within a few light weeks of the event horizon. These are young, massive, hot stars, some of them only a few million years old. That youth is strange because the region near a supermassive black hole is not a place where stars should be forming. The tidal forces are too strong. The radiation environment is too harsh. Gas clouds trying to collapse into stars near the galactic center should be torn apart before they can ignite. And yet there the stars are, bright and blue and impossibly close to the monster at the middle. One explanation is that they formed farther out and migrated inward, possibly as part of a star cluster that got disrupted by interactions with other clusters, or by the black hole itself. Another possibility is that they formed in place under conditions we do not fully understand, in a brief window when the environment near Sagittarius A star was calmer or richer in gas than it is now. Either way, their presence is a puzzle, and the closer astronomers look, the stranger the region becomes. There are plans to observe Sagittarius A star in more detail. Future iterations of the Event Horizon Telescope will include additional radio dishes, improving resolution and allowing for movies rather than single images. A black hole the size of Sagittarius A star flickers on timescales of minutes because the gas orbiting it moves at relativistic speeds. Capturing that variability would let astronomers test predictions from general relativity in the most extreme environments available. Another proposed mission, a space-based interferometer, could image the black hole at even higher resolution, potentially resolving features in the accretion flow that are currently blurred together. And there are ideas for sending probes closer to the galactic center, carrying instruments capable of measuring the gravitational field and magnetic environment near the black hole directly. None of those missions will happen soon. They require technology that does not exist yet and budgets that have not been approved, but the interest is there. Sagittarius A star is close enough and massive enough to serve as a laboratory for physics that cannot be tested anywhere else. If you could watch the region near Sagittarius A star in fast forward, you would see stars drifting inward, some on stable orbits, others on death spirals that will eventually bring them too close. You would see gas clouds heated to millions of degrees as they fall toward the event horizon, glowing briefly in X-rays before vanishing. You would see occasional flares, bursts of radiation when a particularly large clump of matter crosses the point of no return. And you would see, very rarely, a star passing so close to the black hole that tidal forces stretch it into a thin stream of gas, an event called a tidal disruption. Most of those disruptions would be invisible from Earth, hidden behind dust or too faint to detect. But every so often, one would flare brightly enough to light up the galactic center for weeks. We have not witnessed one at Sagittarius A star yet. We have seen them at other galactic centers, in other galaxies, where supermassive black holes briefly outshine their entire host galaxy as they tear apart and consume an unlucky star. It will happen eventually at the Milky Way's center. When it does, every telescope on Earth will turn toward Sagittarius and watch. The black hole is not going anywhere. It will sit at the galactic center for as long as the Milky Way exists. Stars will continue to orbit it. Gas will continue to fall in. The orbits will precess slightly, shifting over thousands of years, as general relativity predicts. The event horizon will grow, very slowly, as the black hole accumulates mass. In a few billion years, when the Milky Way collides with Andromeda, the two supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging into a single, even larger black hole. That merger will release more energy in gravitational waves than all the stars in both galaxies combined emit in light over their entire lifetimes. The ripples from that event will propagate across the universe, stretching and compressing space itself as they pass. And somewhere in the wreckage, a new galaxy will form, anchored by a black hole weighing 10 or 15 million times the mass of the Sun, still growing, still patient, still waiting. For now, Sagittarius A star sits quietly in the dark. It has been there longer than our species has existed. It will be there long after we are gone. It is not malicious. It is not hungry in any way that should concern us. It is just a region of curved space, doing what curved space does, pulling everything nearby a little closer, a little faster, until the pull becomes inescapable. And at the edge of that inescapable region, where space curves so sharply that time itself begins to break, we find the boundary that defines what a black hole actually is. Not a thing, but a threshold. Not a place, but a point of no return. There is a line in space, not a physical line, not something you could paint or touch or mark with a flag. A mathematical line, a boundary carved into the geometry of the universe itself by the presence of extreme mass. Cross that line, and you have not simply entered a dangerous region. You have passed into a place where the concept of leaving stops making sense. Every direction that used to point away now points inward. Every possible future leads to the same destination. The universe you left behind still exists, but it no longer exists for you as somewhere you can go. You have crossed the event horizon. And nothing in physics, no engine, no force, no trick of technology or nature can bring you back. The name itself tells you what it is. An event horizon is the boundary beyond which events can no longer affect an outside observer. Light emitted from beyond that line never escapes. Messages sent from beyond it never arrive. A clock ticking on the far side of the horizon will never be seen to advance by anyone waiting on the outside. The horizon is not a wall. It is not a membrane. It is the point where the future stops connecting to the past in the way it used to. And that point exists because gravity at sufficient strength does not just pull objects together. It bends the stage those objects move on. Imagine space as a stretched rubber sheet. Place a bowling ball in the center and the sheet dips. Roll a marble nearby and it curves toward the bowling ball, following the slope. That is the standard analogy, and it works well enough for gentle gravity. The Earth curves space a little, the Sun curves it more, but a black hole does not just dip the sheet, it punches a hole through it. The curvature becomes so extreme that the slope turns vertical, then worse than vertical. At the event horizon, the shape of space itself folds inward so sharply that every path forward, including the path light takes when moving at its maximum possible speed, leads deeper inside. You have not hit a barrier, the geometry has closed around you. The size of the event horizon depends entirely on the mass of the black hole. More mass means a larger horizon. The relationship is direct. Double the mass, double the radius. The formula comes from general relativity, and it is surprisingly simple. The radius of the event horizon, called the Schwarzschild radius after the physicist who first derived it, is proportional to the mass of the black hole. For a black hole with the mass of our Sun, that radius is about 3 kilometers. Pack one solar mass into a sphere 3 kilometers across, and you have an event horizon. For Sagittarius A star, weighing 4.3 million times the Sun, the radius stretches to about 12 million kilometers. That is roughly 17 times the distance from the Earth to the Sun. A sphere that size could swallow Mercury's entire orbit with room to spare. The event horizon is not glowing. It is not radiating. It does not have a temperature in the classical sense, though quantum mechanics suggests something more complicated happens at microscopic scales, a topic we will leave alone for now. From the outside, the horizon is simply the edge of a region where light cannot escape. If you could somehow paint the event horizon, the paint would fall through it. If you fired a laser at it, the light would cross the boundary and vanish. You would not see a flash. You would not see a reflection. The photons would just stop being part of the universe you can observe. They are still there, in some sense, still moving, still carrying energy. But they are moving in a direction that no longer connects to anything outside. This brings us to a question people ask constantly, and the answer is more subtle than it sounds. What happens if you shine a flashlight toward a black hole? The light travels outward from the flashlight at the speed of light, as light does. If you are far from the black hole, the light moves away from you normally. But as the light approaches the event horizon, something strange happens. The closer it gets, the more the black hole's gravity pulls on it. Not in the sense of slowing it down. Light always moves at the speed of light in its local frame, but the space the light is moving through is curved. From your perspective, far away and safe, the light appears to slow as it nears the horizon. Its wavelength stretches, the frequency drops. What started as visible light redshifts into infrared, then microwave, then radio waves, becoming dimmer and dimmer until it fades from view entirely. The light never quite seems to reach the horizon from your vantage point. It just gets slower and redder and fainter until it disappears. But from the light's perspective, if photons had perspectives, nothing strange happens at all. It crosses the horizon at exactly the speed of light and continues inward without noticing a boundary. This is gravitational redshift, and it is one of the cleanest experimental confirmations of general relativity. The effect is not unique to black holes. Any massive object redshifts light trying to climb out of its gravitational well. The sun does it. The Earth does it. GPS satellites have to account for it, or their clocks would drift out of sync with clocks on the ground. But near a black hole, the effect becomes extreme. At the event horizon, the redshift becomes infinite. A photon trying to escape from exactly the horizon would lose all its energy in the process. Its wavelength would stretch to infinity. It would, in practical terms, cease to exist as light. That is why nothing escapes, not because something is blocking the way, but because the energy cost of climbing out of the gravitational well exceeds the total energy available. The key insight here is that the event horizon is defined by light. Specifically, it is the surface where the escape velocity equals the speed of light. Escape velocity is the speed you need to reach to break free of a gravitational field without using any additional thrust. On Earth, the escape velocity is about 11 kilometers per second. Launch a rocket at that speed and it will coast away from the planet indefinitely, slowing as it climbs but never falling back. The Moon's escape velocity is lower, about 2.4 kilometers per second, because the Moon is less massive. The Sun's is higher, about 618 kilometers per second, because the Sun is much more massive. For a black hole, the escape velocity at the event horizon is exactly 299,792.458 kilometers per second, the speed of light. Get closer, and the escape velocity exceeds the speed of light. And since nothing can move faster than light, nothing can escape. That cutoff is absolute. It does not matter how powerful your rocket is. It does not matter how much fuel you carry. Once you are inside the event horizon, every direction you can point your engines still leads inward. You are not fighting a force. You are trapped in a geometry. The space you are in has been curved so sharply that forward, backward, left, right, up, and down all point toward the center. The only direction that leads out is a direction you can no longer move in. Time, which used to point toward the future, now points toward the singularity. And you will reach that singularity in finite time by your own clock, whether you fire your engines or not. This leads to one of the strangest features of black holes, something that confuses almost everyone who hears about it for the first time. If you watch someone fall toward a black hole, you will never see them cross the event horizon. The light coming from them redshifts as they approach. The signals slow. Their clock, as seen from your safe distance, ticks slower and slower. They appear to freeze just above the horizon, their image fading and redshifting until it becomes too dim to detect. But from their perspective, nothing unusual happens at the horizon. They cross it in finite time. Their clock keeps ticking normally. They do not feel a barrier. They do not see a wall. The horizon is not a place where something dramatic occurs locally. It is a place where the connection between inside and outside breaks. The person falling in continues their journey without noticing the transition. You, watching from outside, lose contact with them forever. Both perspectives are correct. The math supports both. And the tension between those two perspectives has fueled decades of arguments about what a black hole actually is at the deepest level. The no-hair theorem enters here, and the name is unfortunate because it makes the idea sound trivial. It is not. The theorem, proven mathematically in the 1960s and 70s, states that a black hole in equilibrium is completely described by exactly three properties: mass, spin, and electric charge. That is it. Every other detail about the matter that formed the black hole, its composition, its shape, its history, the exact sequence of events that led to its collapse, all of it gets erased. A black hole made from collapsing hydrogen looks identical to a black hole of the same mass made from collapsing iron. A black hole formed from a star looks identical to one formed from a direct collapse of primordial gas, assuming the mass, spin, and charge are the same. The theorem tells you that black holes have no hair, no distinguishing features, no fine details, just three numbers. In practice, astrophysical black holes have essentially no charge because matter is electrically neutral on large scales and any excess charge gets neutralized quickly. So really, black holes are described by two numbers: mass and spin. That is all the universe remembers. This seems strange until you realize what it is saying. The event horizon hides everything behind it. No information about the interior can escape to the outside. So from an external perspective, the only things that matter about a black hole are the things you can measure from outside. You can measure its mass by watching how things orbit it. You can measure its spin by watching how space is dragged around it. And if it had charge, you could measure that with electromagnetic fields. But you cannot measure the temperature of the core, or the density distribution, or the chemical composition, because none of those things produce signals that escape the horizon. The no-hair theorem is not just a mathematical curiosity. It is a direct consequence of the event horizon being a one-way boundary. Information goes in, it does not come out. So the only properties that matter are the ones imprinted on the external spacetime. Spin matters more than most people realize. Every black hole spins. Angular momentum from the collapsing star gets conserved, and because the core shrinks to such a small size, the rotation rate increases dramatically. A slowly rotating star collapses into a rapidly spinning black hole. The fastest spinning black holes rotate at nearly the speed of light at their event horizons. When a black hole spins, it drags spacetime around it in a process called frame dragging. Close to the black hole, space itself is rotating. If you tried to remain stationary near a spinning black hole, you would find that you cannot. Space is moving, and you are embedded in it, so you get dragged along. This region where frame dragging dominates is called the ergosphere, and it sits just outside the event horizon. In principle, you can enter the ergosphere and escape, though doing so requires precise maneuvering. The event horizon itself, for a spinning black hole, is not a perfect sphere. It bulges slightly at the equator and flattens at the poles, shaped by the rotation. The size of the event horizon changes with spin. For a non-rotating black hole, the radius is exactly the Schwarzschild radius. For a maximally spinning black hole, the event horizon shrinks to half that size. The faster the black hole spins, the smaller the horizon becomes, up to a theoretical limit where the black hole cannot spin any faster without violating the laws of physics. No one has ever observed a black hole spinning at that maximum rate, but some come close. Measurements of spin for several supermassive black holes suggest rotation rates above 90% of the maximum. Sagittarius A star is estimated to spin at a more modest rate, but the uncertainty is large. Measuring spin requires detailed observations of the material orbiting just outside the event horizon, and those observations are difficult even with the best instruments we have. One of the most persistent misconceptions about the event horizon is that it is a place of extreme violence. People imagine crossing the horizon as stepping through a furnace or hitting a wall of radiation. That is not correct. For a large black hole, the event horizon is, locally, unremarkable. The tidal forces at the horizon of a supermassive black hole are surprisingly gentle. For a black hole with 10 million solar masses, the tidal force at the event horizon is roughly equal to the gravity you feel standing on Earth. You would not be torn apart. You would not even feel uncomfortable. The reason is that tidal forces depend on the gradient of the gravitational field, how quickly gravity changes over distance. For a very large black hole, the event horizon is far from the center, and the gradient at that distance is relatively mild. You could cross the horizon of a supermassive black hole without immediate physical distress. The destruction comes later, deeper inside, as you approach the singularity. But at the horizon itself, nothing dramatic happens. You cross a line in space-time. The universe behind you becomes unreachable, and you continue falling. That is perhaps the most unsettling part. The event horizon is not a barrier. It does not resist. There is no moment of impact, no sensation of crossing over. If you are falling toward a black hole, instruments and all, the moment you cross the horizon would pass without any local indication that something fundamental had just changed. Your clock would keep ticking. Your instruments would keep recording. The stars behind you would still be visible, though increasingly distorted by gravitational lensing. You would not feel a jolt. You would not hear a sound. The only way you would know you had crossed the horizon is if you tried to turn around and found that you could not. Every signal you send back toward the outside would fail. Every thrust of your engines, no matter how powerful, would only change the details of your trajectory inward, not reverse it. You are past the point of no return, and the physics of that point is simply this. The future no longer includes the outside universe. Your future is the singularity, and you will reach it in seconds, or minutes, or hours, depending on the black hole's mass, but you will reach it. There is no known way to stop the infall once you are inside. Proposals involving exotic matter, or wormholes, or quantum effects all run into the same problem. The space-time inside the event horizon does not allow for trajectories that lead outward. General relativity is clear on this. The math has been checked and rechecked for over a century. If general relativity is correct, and every test we have ever performed says it is, then crossing the event horizon ends your connection to the outside universe permanently. You do not get to send a message. You do not get to leave a note. You fall, and the universe you left behind continues without you. Some researchers have speculated about whether quantum mechanics might change this picture. The idea is that quantum effects near the horizon could allow information to escape in ways that classical general relativity does not account for. This is the core of the black hole information paradox, a deep and still unresolved question in theoretical physics. Stephen Hawking famously showed in the 1970s that black holes should emit radiation due to quantum effects near the event horizon, a process now called Hawking radiation. If that radiation carries information about what fell into the black hole, then the no-return rule might have loopholes at the quantum level. But even if Hawking radiation is real, and the theoretical case for it is strong, the effect is extraordinarily weak. For a black hole the size of Sagittarius A star, the Hawking radiation would have a temperature far below the cosmic microwave background. The black hole would absorb more energy from the universe than it radiates. It would take longer than the current age of the universe for a solar mass black hole to evaporate via Hawking radiation, and for a supermassive black hole, the timescale stretches to 10 to the 100 years or longer. Even if quantum mechanics provides a theoretical escape route, it is not one you could use. The event horizon is a threshold, not a place, but a dividing line between two kinds of futures. On one side, the future includes the possibility of escape, of returning home, of existing indefinitely in the wider universe. On the other side, the future narrows to a single destination. You can delay it, you can struggle against it, but the geometry will not bend. The singularity is in your future the same way tomorrow is in your future. Inevitable, unreachable from the outside, inescapable from the inside. And the border between those two futures, the place where the equations shift and the possibilities collapse, is a sphere of empty space marked only by the fact that light itself cannot climb back out. If you were somehow able to measure the space-time curvature as you approached the event horizon, your instruments would show the curvature increasing smoothly. There is no discontinuity at the horizon. The geometry does not jump. It curves more and more sharply until, at the horizon, the curvature reaches the critical point where outward paths stop existing. Move a little closer and the curvature becomes more extreme. The tidal forces grow, the singularity looms, but the horizon itself is smooth. It is a coordinate singularity in some reference frames, a place where certain ways of describing space-time break down mathematically, but the physical space-time is perfectly well behaved. An object falling through the horizon does not encounter infinite forces or infinite curvature. Those come later. The horizon is just the edge of the region where the inside is sealed off from the outside, and once you are inside, the only way forward is down. You are falling, not toward Earth, where air resistance would slow you, and eventually a parachute or the ground would stop the descent. You are falling toward a black hole, and there is no air, no parachute, no ground, just geometry. The space you are moving through is curved, and the curve gets steeper with every passing second. Your velocity increases. The black hole grows larger in your field of view, or more accurately, the distortion it causes in the star field behind it grows larger, a circular patch of darkness rimmed by a thin halo of bent light. You are still outside the event horizon. You have not yet crossed the point of no return. And already something is wrong. Your feet hurt. Not a dull ache, not the kind of discomfort you get from standing too long. A sharp, pulling sensation, as if someone has grabbed your ankles and is yanking downward with increasing force. At the same time, your shoulders feel compressed, squeezed inward, as though the walls of a room are slowly closing in on you. The pain intensifies. Your spine stretches. Your legs elongate. The distance between your head and your feet, which has remained roughly the same for your entire life, starts to increase. You are being pulled apart. This is spaghettification, and it is not a metaphor. The term sounds absurd. It sounds like something a science fiction writer made up to sell books, or a joke physicists tell at conferences after too many drinks. But the phenomenon is real, the name is official, and the process is exactly what it sounds like. You are being turned into a strand, not quickly, not cleanly, but inevitably. The black hole is not grabbing you, It is not exerting some mysterious sucking force. It is simply sitting there, warping space, and you are falling through that warped space under the influence of gravity. The problem is that gravity is not uniform. It gets stronger the closer you get to the source. And because your feet are closer to the black hole than your head, they experience a stronger pull. That difference, that gradient in gravitational strength across the length of your body, is what tears you apart. This is a tidal force. The name comes from ocean tides on Earth, which are caused by the same mechanism. The side of the Earth facing the Moon experiences slightly stronger gravity than the side facing away, because it is closer. That difference pulls the oceans into a bulge. The effect is gentle because the Moon is far away and not particularly massive. The gradient is small. But scale up the mass and shrink the distance, and the gradient becomes extreme. Near a black hole, the tidal force is not pulling ocean water into a bulge. It is pulling you into a thread. The strength of the tidal force depends on two things: how close you are to the black hole and how massive the black hole is. The closer you get, the stronger the force. That part is intuitive, but the second part is counterintuitive. The more massive the black hole, the weaker the tidal force at the event horizon. This is one of the strangest features of black holes, and it catches almost everyone off guard. A small black hole will spaghettify you long before you reach the event horizon. A supermassive black hole will let you cross the horizon intact and only tear you apart deeper inside. The reason comes down to the size of the event horizon relative to the mass. For a black hole with the mass of our Sun, the event horizon has a radius of about 3 kilometers. The singularity, the point at the center where all the mass is concentrated according to general relativity, sits at the very middle. 3 kilometers is not much distance. If you are falling feet first toward a solar mass black hole and your body is about 2 meters tall, then when your feet are at the event horizon, your head is 2 meters farther out. That 2-meter difference, across a distance where gravity is changing incredibly rapidly, results in an enormous tidal force. The equations tell you that the tidal force at the event horizon of a solar mass black hole would be strong enough to tear a human body apart long before reaching the horizon. You would be spaghettified while still outside, stretched into a thin stream of atoms, dead long before you crossed the boundary. Now scale up to a supermassive black hole. Sagittarius A star, sitting at the center of the Milky Way, weighs about 4 million times the mass of the Sun. Its event horizon has a radius of roughly 12 million kilometers. The singularity is still at the center, but the horizon is much, much farther away from it. When you are falling towards Sagittarius A star and your feet reach the event horizon, your head is still 2 meters farther out. But 2 meters across a distance of 12 million kilometers is nothing. The gradient is gentler. The tidal force at the horizon is weak. Calculations show that the tidal force at the event horizon of a black hole with 10 million solar masses is comparable to the gravitational difference between your head and your feet standing on Earth. Noticeable if you had sensitive enough instruments, but not dangerous. You could cross the event horizon of a supermassive black hole without being torn apart. The spaghettification comes later, as you continue falling inward and the distance to the singularity shrinks. This is not obvious. Most people assume that crossing the event horizon is the moment of destruction, that the boundary itself is lethal. It is not. The event horizon is just a mathematical surface, a point of no return. The tidal forces depend on how tightly curved the space is, and for a very massive black hole, the curvature at the horizon is relatively gentle. The violence happens closer to the center, where the curvature becomes extreme regardless of the black hole's mass. But for a supermassive black hole, you get a grace period. You cross the horizon, still alive, still intact. And you have time, maybe minutes, maybe longer, depending on the mass, before the tidal forces grow strong enough to kill you. That grace period does not exist for smaller black holes. A stellar mass black hole, the kind formed from the collapse of a massive star, weighs only a few times the mass of the Sun. The event horizon is tiny. The tidal forces at the horizon are immense. You would not survive the approach. Long before your feet touched the horizon, the difference in gravitational pull between your feet and your head would exceed the tensile strength of human tissue. Your bones would snap, your muscles would tear, your blood vessels would rupture, and the process would not stop there. The tidal force would continue pulling, stretching what used to be your body into a thinner and thinner strand, breaking it down past the level of tissues, past the level of cells, eventually past the level of molecules. By the time the remains of your body crossed the event horizon, they would no longer be recognizable as a body, just a stream of atoms falling inward in a line. The equations that describe tidal forces are straightforward. The force is proportional to the mass of the black hole, the size of the object being stretched, and inversely proportional to the cube of the distance from the center. That inverse cube dependence is what makes the effect so dramatic. Move twice as close, and the tidal force increases by a factor of 8. Move 10 times closer, and the force increases by a factor of 1,000. The gradient grows steeper and steeper as you approach the singularity, and eventually it becomes infinite. At the singularity itself, assuming general relativity is correct all the way down, the tidal force is infinite. Anything that reaches that point is compressed to zero volume and infinite density. But you do not have to reach the singularity to be destroyed. The tidal forces become lethal long before that. Let us put numbers on this to make it concrete. A human body is roughly 2 meters tall and can withstand tension forces of a few thousand newtons before bones start breaking. The tidal force you experience depends on the gradient of gravity across your height. For a black hole with 10 solar masses, the event horizon sits at about 30 kilometers from the center. At that distance, the tidal force on a 2-meter tall human body is already in the range of millions of newtons. You would be torn apart instantly, long before reaching the horizon. For a black hole with 1 million solar masses, the event horizon sits at about 3 million kilometers. The tidal force at the horizon is much weaker, maybe a few newtons across your height. Uncomfortable, but survivable. For a black hole with 1 billion solar masses, the tidal force at the horizon is negligible. You would not feel anything unusual crossing it. The black hole is so large that the curvature of space at the horizon is gentle, almost flat. You would fall through the boundary without noticing, at least not from the tidal forces. Time dilation would be another matter, but we are not there yet. The shape you are stretched into depends on the direction of the tidal force. Gravity pulls along the radial direction, toward the center of the black hole. That is the direction you are being stretched. At the same time, the geometry of space around a spherical mass compresses objects in the directions perpendicular to the radial. Think of it this way: gravity pulls inward from all sides. As you fall, the pull from the sides is directed toward the center, which means it squeezes you horizontally while pulling you apart vertically. You do not just get longer, you get thinner. The cross-section of your body shrinks as you are stretched. The overall effect is that you are deformed into a long, thin strand, like a piece of spaghetti, hence the name. The process is not instantaneous, it happens over time, and the time scale depends on how strong the tidal forces are. Near a stellar mass black hole, the stretching happens over the course of a few seconds or less. Near a supermassive black hole, it could take minutes or even longer, depending on how deep inside the event horizon you are when the forces become severe. During that time, you would be conscious, at least initially. Your brain would still be receiving signals from your body, at least until the damage became so extensive that the nervous system stopped functioning. You would feel the stretching. You would feel the pain. You would be aware that something was pulling you apart, that your body was deforming in ways it was never meant to deform. And then, eventually, the signals would stop. The neurons would tear. The synapses would break. Consciousness would end, not because your brain stopped trying to function, but because the physical structure required for thought would no longer exist in one piece. The atoms that used to make up your body do not vanish. They continue falling. Once separated into individual atoms or small molecules, they experience their own tidal forces, but atoms are much more resilient than human tissue. The electromagnetic forces holding atoms together are strong enough to resist tidal forces until you get very close to the singularity. So the stream of atoms that used to be you continues inward, stretched into a thinner and thinner line, spiraling slightly if the black hole is rotating, accelerating as it falls. Eventually, even atoms cannot survive. Near the singularity, the tidal forces exceed the binding energy of atomic nuclei. Protons and neutrons get torn apart into quarks. The quarks themselves might be torn apart if they are composite, though we do not know enough about physics at that scale to say for sure. At some point, the structure of matter breaks down completely, and what remains is a question that general relativity cannot answer because the equations break down at the singularity. But all of that is academic. The important part, the part you would experience if you were somehow falling into a black hole, is that the stretching begins long before you reach the singularity and long before the physics becomes uncertain. The tidal forces become lethal at distances that are perfectly well described by general relativity, distances where the math works and the predictions are clear. You do not need quantum gravity to understand spaghettification. Classical general relativity handles it just fine. The equations tell you exactly how strong the tidal force is at any given distance from any given mass. Plug in the numbers and you get an answer. The answer, for a human body near a black hole of a few solar masses, is death by stretching within seconds of approaching the event horizon. For a supermassive black hole, the answer is a few minutes of free fall after crossing the horizon before the forces become lethal. Either way, the outcome is the same. You are torn apart. The only question is when. It is worth pausing to ask whether there is any way to avoid this. The short answer is no. The tidal force is a consequence of the geometry of space around a massive object. You cannot turn it off. You cannot shield against it. Some people imagine that a strong enough spacesuit or a rigid enough container could protect you, but that does not work. The tidal force acts on every part of your body individually. It is not a force applied to your surface that you could resist with armor. It is gravity pulling on every atom, and the atoms closer to the black hole are pulled harder than the atoms farther away. A rigid container would just get stretched along with you. The walls of the container would experience the same tidal forces. They would deform, crack, and eventually tear. You cannot build a structure strong enough to resist infinite tidal forces near a singularity. And even if you could, you would still be inside a container that is falling toward the singularity, and the singularity is a place where the container and you and everything else gets compressed to a point. Some theoretical proposals involve using a spaceship with an extremely powerful engine to counteract the inward pull, hovering at a fixed distance from the black hole. This is possible in principle outside the event horizon, though it requires an enormous amount of thrust. The closer you hover to the horizon, the more thrust you need. At the horizon itself, you would need infinite thrust, which is another way of saying it is impossible. Inside the horizon, it does not matter how powerful your engine is. Every direction you can point it still leads inward. The geometry does not allow for stationary hovering inside the event horizon. You are falling, and the tidal forces will eventually tear apart both you and your spaceship. The only scenario where you might delay spaghettification is if you are falling into an extremely massive black hole. The supermassive black holes at the centers of galaxies, the ones weighing billions of times the mass of the Sun, have event horizons so large that the tidal forces at the horizon are almost undetectable. You could cross the horizon and continue falling for minutes or even hours before the tidal forces became dangerous. During that time, you would be inside the black hole, past the point of no return, but still alive and intact. You would have time to look around, to take measurements, to experience being inside an event horizon. Not that it would do you any good. The measurements could not be sent back out. The experience could not be shared. And eventually, as you fell closer to the singularity, the tidal forces would grow and the stretching would begin, and the outcome would be the same as it is for any black hole. You would be torn apart. The only difference is that you would get a longer look at the inside before it happened. There is a certain horror to the precision of this process. Spaghettification is not random, it is not chaotic. It is a clean, deterministic consequence of the equations that describe gravity. Given the mass of the black hole and the size of the object falling in, you can calculate exactly how strong the tidal forces will be at any point along the fall. You can predict, to high precision, the moment when bones will break, when tissues will tear, when cells will rupture. You can map out the entire sequence of destruction in advance. The universe does not care about your comfort or your survival. It cares about geometry, and the geometry near a black hole is shaped in a way that pulls things apart. The visual image most people carry of spaghettification is someone being stretched vertically into a long thin line, like taffy being pulled. That image is mostly correct, but it misses the compression. You are not just stretched, you are squeezed. The horizontal dimensions of your body shrink as the vertical dimension grows. If you could somehow watch yourself being spaghettified from an outside perspective, which you cannot, but if you could, you would see your body elongate while simultaneously narrowing. Your width and depth would decrease. Your limbs would thin. Your torso would stretch into a cylinder, then into a rod, then into a thread. The cross-sectional area would drop. The overall shape would become less and less recognizable as anything that used to be human. Eventually, you would look like a piece of string, then a hair, then a line of atoms, and then, closer to the singularity, not even that. Just a smear of energy, compressed and stretched beyond any meaningful structure. None of this is visible from the outside. If someone far from the black hole were watching you fall, they would see you approach the event horizon, slow down as gravitational time dilation took effect, and then freeze, your image redshifting and fading until it disappeared. They would never see you cross the horizon. They would never see you get stretched. The spaghettification happens inside, in a region of space-time that is causally disconnected from the outside universe. The light from the stretching, the photons that would carry the image of your elongated body never escape. They fall inward along with you. So from an external perspective, you just vanish. From your perspective, you are torn apart. Both perspectives are correct, and both are described by the same mathematics. The fact that larger black holes are gentler near their event horizons has an interesting implication. If you wanted to study the interior of a black hole, your best chance would be to fall into a supermassive one. A stellar mass black hole would kill you before you learned anything. A supermassive black hole would give you time. Not much time, and not enough time to report back, but time to observe, to experience, to exist for a brief window inside a region of space-time that the rest of the universe can never access. Some physicists have speculated about what you might see during that window. The answer depends on poorly understood physics, but the journey itself, the inward fall, would be described by general relativity all the way until the tidal forces or the approach to the singularity made the description break down. For most of the fall, the physics is known, the outcome is not. Spaghettification is the mechanism, tidal forces are the cause, gravity is the driver, and time, which has been running normally for you during the entire fall so far, is about to become the strangest part of the experience. Because as you fall deeper into the black hole's gravitational well, not only does space curve more sharply, but time itself starts to stretch and warp in ways that break every intuition you have ever developed about how clocks work, how fast events happen, and what it means for two things to occur at the same moment. You are still falling. The tidal forces have not killed you yet, which means you are either very lucky or you are falling into a black hole so massive that spaghettification is still minutes away. Your body is intact. Your instruments, assuming you brought any, are still functioning. And as you fall deeper into the gravitational well, accelerating with every passing second, you begin to notice something stranger than the stretching, stranger than the darkness expanding in your field of view, stranger than the distorted halo of light surrounding the event horizon. Your watch is running slow, not broken, not damaged, just slow. You can see the second hand ticking forward, one beat at a time, but the interval between ticks feels longer than it should. You look at the readout on your instruments, the atomic clock you brought along specifically because atomic clocks are supposed to be the most stable timekeepers humanity has ever built. It is ticking slower than it should relative to your own perception of time. Or more accurately, you are ticking faster. Or perhaps neither description is correct, because the whole question of who is ticking at the right rate has stopped making sense. You have entered a regime where time itself is no longer uniform, where clocks in different locations disagree not because one of them is broken, but because time is running at different speeds depending on where you are and how deep you are inside a gravitational field. This is gravitational time dilation. It is not a malfunction, it is not a measurement error. It is one of the core predictions of general relativity, Einstein's theory of gravity, and it has been tested so many times in so many ways that calling it a prediction almost feels unfair. It is an observed fact. Clocks run slower in stronger gravitational fields, always, without exception. The effect is tiny on Earth, noticeable near a neutron star, extreme near a black hole, and at the event horizon of a black hole, from the perspective of someone far away, time does not just slow down, it stops. Let us back up, because the idea that time can run at different rates depending on where you are sitting is not intuitive. You have spent your entire life experiencing time as a universal constant. Seconds tick by at the same rate whether you are standing on a mountain or sitting in a basement. An hour is an hour. A day is a day. The universe, as far as everyday experience is concerned, runs on a single clock. That assumption is wrong. It is close enough to correct for most purposes that you never notice the difference, but it is wrong. And near a black hole, the wrongness becomes impossible to ignore. Einstein figured this out in 1915 when he published the general theory of relativity. The theory replaced Newton's picture of gravity as a force pulling objects together with a new picture where gravity is not a force at all, but a curvature of space-time itself. Mass and energy warp the fabric of space and time. Objects moving through that warped spacetime follow curved paths, and we call those paths orbits or freefall, depending on the situation. The key insight, the one that changes everything, is that time is part of the fabric. Space and time are not separate. They are woven together into a single structure called spacetime. And when mass curves space, it curves time as well. The mathematical framework is complicated. The equations are dense, but the physical consequences are surprisingly concrete. If you place a clock deep inside a gravitational well and compare it to a clock far from any massive object, the clock in the well runs slower, not because the mechanism is faulty, because time itself is passing more slowly at that location. The clock is measuring time correctly. Time is just different there. This was tested experimentally less than 50 years after Einstein published the theory. In 1959, Robert Pound and Glenn Repka conducted an experiment at Harvard University using gamma rays emitted by radioactive iron. They placed a gamma-ray source in the basement of a building and a detector on the roof, 22.5 meters higher. The gamma rays traveling upward, climbing out of Earth's gravitational well, lost a tiny amount of energy. The amount was minuscule, a shift of about 1 part in 10 to the 15th, but it was detectable, and it matched Einstein's prediction exactly. Photons climbing out of a gravitational field lose energy, their frequency decreases. This is gravitational redshift, and it is the flip side of time dilation. If time runs slower, deep in a gravitational well, then clocks there tick slower, and light emitted from there appears redshifted to an observer higher up. The effect scales with the strength of the gravitational field. On Earth, the difference in the rate of time between the basement and the roof of a building is so small that it only matters for precision experiments. GPS satellites have to account for it because they orbit at an altitude where Earth's gravity is slightly weaker than it is on the surface. The clocks on the satellites run faster than clocks on the ground by about 38 microseconds per day. If the GPS system did not correct for this, the positioning errors would accumulate at a rate of about 10 kilometers per day. Your phone knows where you are because engineers programmed general relativity into the satellites. Near a neutron star, the effect becomes dramatic. Neutron stars are the densest objects in the universe that are not black holes. They pack about 1.4 times the mass of the Sun into a sphere roughly 20 kilometers across. The surface gravity is so strong that a clock on the surface of a neutron star runs noticeably slower than a clock in orbit around it. An astronaut standing on the surface, assuming they could survive the gravity and radiation, which they could not, would age more slowly than an astronaut orbiting above. The difference would be measurable in seconds per hour. Spend a day on the surface, and you would be minutes younger than someone who spent the same day in orbit. Near a black hole, the effect goes off the scale. Time dilation near a black hole is so extreme that it breaks the ordinary language we use to talk about time. An observer far from the black hole, watching someone fall toward the event horizon, sees the infalling person slow down as they approach. The light from the falling observer becomes redshifted. The signals they send back arrive at longer and longer intervals. Their clock, as seen from a distance, ticks slower and slower. At the event horizon, from the perspective of the distant observer, time stops completely. The falling observer appears to freeze just above the horizon, their image fading and redshifting into invisibility. They never seem to cross. Not in 10 seconds, not in 10 years, not ever. As far as the distant observer is concerned, the event horizon is a surface where time has stopped, and anything approaching it takes infinite time to reach it. But that is only one perspective. From the perspective of the person falling in, nothing unusual happens at the horizon. Their own clock keeps ticking normally. They do not feel time slowing down. They do not freeze. They cross the event horizon in finite time by their own measure. A few seconds, maybe a few minutes, depending on the mass of the black hole and the details of their trajectory. The event horizon is not a place where they get stuck. It is a place they pass through, and once they pass through, they continue falling inward. To them, time is running normally. The watch on their wrist ticks at the same rate it always did. Their heart beats at the same rhythm. Their neurons fire at the same speed. Locally, everything is normal. So who is right? The distant observer who sees time stop at the horizon, or the infalling observer who crosses it without noticing? The answer is both. They are both correct. They are describing the same event from different reference frames, and general relativity says that time is frame-dependent. There is no universal clock. There is no objective answer to the question of how much time passes between two events, unless you specify which observer is asking. The distant observer and the infalling observer are embedded in different parts of the curved spacetime around the black hole, and the geometry of that spacetime determines how they measure time. Their clocks are both working correctly. They just disagree. This disagreement is not a paradox. It is a feature of the theory. General relativity does not say that time is the same everywhere. It says that time is part of spacetime, and spacetime is curved by mass, and observers moving through different regions of curved spacetime will measure time differently. The distant observer sees the infalling observer slow down and freeze because the light from the infalling observer is climbing out of a deeper and deeper gravitational well, losing energy and redshifting in the process. The infalling observer does not see themselves slow down because they are moving with their own clock. Both descriptions are valid, both are predictions of the same equations, and both have been confirmed indirectly by observations of objects orbiting near black holes and by measurements of time dilation in other strong gravitational fields. The mathematics behind this is surprisingly clean. The amount of time dilation depends on a quantity called the gravitational potential. Closer to a massive object, the potential is deeper and time runs slower. The relationship is given by a factor that appears in the metric, the mathematical object that describes the shape of spacetime. For a non-rotating black hole, the metric is called the Schwarzschild metric, named after Carl Schwarzschild, who derived the solution to Einstein's equations for a spherical, non-rotating mass just months after general relativity was published. Schwarzschild did this while serving in the German army during World War I. He sent his solution to Einstein from the Russian front. He died of an illness a few months later. His solution is still used today to describe the spacetime around black holes. The Schwarzschild metric contains a term that goes to zero at the event horizon. That term determines how much proper time, the time measured by a clock moving along a specific path, corresponds to coordinate time, the time measured by a distant observer using a coordinate system. As you approach the event horizon, the ratio between proper time and coordinate time changes. For the distant observer, the coordinate time it takes for something to reach the horizon is infinite. For the infalling observer, the proper time is finite. The difference arises because the coordinates themselves behave strangely near the horizon. The Schwarzschild coordinates, which work fine far from the black hole, break down at the horizon in a way that makes it look like time stops there. But the breakdown is in the coordinates, not in the spacetime. Switch to a different coordinate system, one that does not have this problem, and the event horizon is perfectly smooth. The infalling observer crosses it without difficulty. This is a coordinate singularity. The term sounds technical, but the idea is simple. A coordinate singularity is a place where your description of space-time breaks down, but the space-time itself is fine. An analogy that gets used often is the North Pole on Earth. If you use latitude and longitude to describe positions on the globe, the North Pole is a problem. Longitude is undefined there. Every direction is south. The coordinates break. But there is nothing physically wrong with the North Pole. You can walk to it. You can stand on it. The problem is with the coordinate system, not with the location. The event horizon of a black hole is similar. Schwarzschild coordinates make it look like time stops there. But that is an artifact of the coordinates. The space-time is smooth. The physics is well behaved. The infalling observer crosses without encountering infinite forces or infinite curvature. Those come later, near the singularity. From the perspective of someone far from the black hole, watching a star or a cloud of gas fall toward the event horizon, the object never quite reaches it. The light from the object redshifts, the signals slow, the object dims and fades. Eventually, it becomes too faint to detect, but it never crosses. As far as the distant universe is concerned, everything that has ever fallen toward a black hole is still falling, frozen in time just above the horizon. This leads to a strange conclusion. If you could somehow see all the light that has ever been emitted by objects falling into a black hole, you would see a thin shell of frozen images just above the event horizon, a graveyard of everything the black hole has ever consumed, all of it stuck in the last moment before crossing. In practice, you do not see this because the light is so redshifted and dim that it becomes undetectable almost immediately. But in principle, it is there. For the infalling observer, the picture is different. They see the event horizon approach and then pass. They do not see it as a surface. They do not see a shell of frozen objects. They just see the distorted star field around them, the blackness growing larger, and eventually, after crossing, the stars disappearing from view as the light cones tilt inward and no light from outside can reach them anymore. The crossing itself is uneventful. The drama, if there is any, comes from what they see happening to the outside universe as they fall. As the infalling observer accelerates toward the event horizon, time dilation works both ways. From their perspective, the outside universe speeds up. Clocks far from the black hole run faster. Events that would take years or centuries in the outside universe happen in compressed time from the perspective of the falling observer. If they could watch a star orbiting the black hole, they would see it speed up, completing its orbit in less and less time as they fell deeper. If they fell for long enough, they would see the star complete many orbits in what felt like a few minutes to them. Theoretically, if they could survive long enough, and if the black hole were large enough that tidal forces did not kill them immediately, they could watch the far future of the universe unfold in fast forward as they fell. This is the flip side of the distant observer seeing the infalling observer freeze. The infalling observer sees the distant observer speed up. Both effects are real. Both are consequences of the same geometry. The distant observer sees time stop at the horizon. The infalling observer sees time in the outside universe accelerate without limit. At the moment of crossing the event horizon, the infalling observer, in principle, sees the entire future history of the outside universe compressed into an instant. They see the stars evolve, die, the galaxies drift apart, the universe cool and darken, all in the last fraction of a second before the event horizon closes behind them. This does not happen in practice because the light from the distant universe gets redshifted and dimmed to the point where it is undetectable long before you reach that extreme. But the mathematics says it should happen. The equations predict that the infalling observer at the horizon has access in principle to signals from arbitrarily far into the future of the outside universe, all compressed into their final moments before crossing. This effect has been the subject of intense debate among physicists. Some argue that quantum effects near the horizon might disrupt this picture, that the classical description breaks down and something else happens that we do not yet understand. Others argue that the classical description is perfectly valid, that general relativity handles the horizon just fine, and that the strange predictions about seeing the future are correct within the framework of the theory. The debate is not settled. What is settled is that time dilation near black holes is extreme, that the distant observer and the infalling observer measure time very differently, and that both measurements are valid within their own reference frames. For practical purposes, this means that anything falling into a black hole is lost to the outside universe, not just spatially, but temporally. The distant universe moves on, time continues, but for the object that fell in, time has diverged. The outside universe races ahead, and the infalling object is left behind, frozen in the reference frame of the outside observer, even though from its own perspective it crossed the horizon and continued inward. The two timelines split. They stop being comparable. The distant observer can no longer assign a meaningful time coordinate to events happening inside the horizon, because those events are not in the causal future of the distant observer. They are in a separate region of space-time, one that the distant observer can never access or receive signals from. This has implications for the idea of rescuing someone who has fallen into a black hole. Even if you had a way to reach inside the event horizon, which you do not, you would face a time problem. By the time you organized a rescue and accelerated toward the black hole, the person you are trying to rescue would have fallen much deeper inside. From their perspective, time is still moving forward. They have crossed the horizon and are now falling toward the singularity. From your perspective, they are frozen just above the horizon. You cannot catch up to them because you are operating in a different time frame. The geometry does not allow for it. The rescue mission fails not because you lack the technology, but because the space-time does not permit a path from your location to theirs. The event horizon is a one-way boundary in time as much as it is in space. This temporal disconnection is one of the reasons black holes are so final. It is not just that you cannot escape once you cross the horizon. It is that the outside universe, the place you came from, stops being part of your future. The only future available to you is the singularity. And the outside universe, for its part, stops being able to assign a meaningful time to your ongoing experience. You have left the shared timeline. You are still experiencing time, still moving forward through your own proper time, but that time no longer synchronizes with the time in the outside universe. You have diverged. For space travel, time dilation near black holes is both a hazard and, theoretically, an opportunity. The hazard is obvious. If you send a mission close to a black hole, the crew will experience time differently than mission control. A few hours near the event horizon could correspond to years or decades back on Earth. The crew returns younger than the people who sent them. This is the classic twin paradox taken to the extreme. One twin stays home, the other twin travels close to a black hole and returns. The traveling twin has aged less. The effect is not symmetric. The twin who traveled through the stronger gravitational field aged more slowly. The math is clear. The predictions are testable, and if we ever develop the technology to send humans near black holes, this will be a real operational issue, not a thought experiment. The opportunity, if you can call it that, is time travel into the future. If you want to see what the universe looks like in 1,000 years, you could in principle fly close to a black hole, orbit near the event horizon for a subjective period of a few days or weeks, and then return. When you arrive back at Earth, 1,000 years will have passed. You will have aged a few weeks. Everyone you knew will be dead. Civilizations will have risen and fallen. The stars will have shifted in the sky. You will have traveled into the future without violating any laws of physics. General relativity allows it. The technology to do it does not exist, and the energy cost would be absurd, but the physics permits it. Time dilation is a one-way time machine, always pointing forward, never back. For interstellar communication, time dilation introduces delays that are not just about the speed of light. If a probe is orbiting near a black hole and sends a signal back to Earth, the signal will be redshifted and delayed not just by the distance, but by the time dilation. A signal that takes 1 second to transmit from the probe's perspective might take minutes or hours to arrive at Earth, stretched out in time by the gravitational field. The frequency of the signal drops, the data rate decreases. Mission planners would have to account for this. They would have to build protocols that assume time is not synchronized between the probe and the ground station. Every message would carry a timestamp, and those timestamps would disagree. The probe's clock would say one thing, Earth's clock would say another. Both would be correct. This is not science fiction. This is general relativity. Time dilation is a measured, confirmed, repeatedly tested prediction of the theory. It shows up in GPS satellites. It shows up in particle accelerators, where fast-moving particles decay more slowly than stationary ones, an effect called kinematic time dilation, which is related but distinct from gravitational time dilation. It shows up in precision atomic clocks flown on airplanes. Every test confirms the same thing. Time is not absolute. Time is malleable. And near a black hole, time becomes so stretched and warped that the ordinary rules of before and after, past and future, start to lose their meaning. You are still falling, and by now, if you are falling toward a supermassive black hole, you have crossed the event horizon. From your perspective, nothing dramatic happened. The boundary came and went. Your clock kept ticking. But behind you, the outside universe has raced forward. The stars you were looking at a moment ago have aged. Galaxies have drifted. The timeline you were part of has split off, and you are now in a region of space-time that is disconnected from the future of the outside universe. You are inside the event horizon, and ahead of you, deeper inside, lies a place where the known laws of physics stop making predictions, where the mathematics of general relativity breaks down, where the structure of space-time itself becomes so distorted that no one knows what happens next. That place is the singularity, and it is the only future you have left. You are inside. That fact alone should be impossible to state, because the words "you" and "inside" imply an observer and a location, and inside a black hole, both concepts start to fracture. But for the moment, let us pretend the language still works. You have crossed the event horizon. From your perspective, the crossing was smooth. No barrier, no jolt, no sensation that anything fundamental had changed. Your clock kept ticking. Your heart kept beating. The instruments around you, assuming you brought any, and assuming they survived the journey this far, are still recording data, and yet something has changed, something profound. You are now in a region of space-time that is causally disconnected from the rest of the universe. The photons you emit, the radio signals you send, the light from your body, all of it is trapped with you, falling inward, unable to climb back out. You are sealed inside a geometric prison, and the walls of that prison are not made of matter or energy, they are made of time itself. The first thing to understand about the interior of a black hole is that the usual rules about space and time have swapped roles. Outside the event horizon, time points toward the future, and space points in directions you can move. You can go left or right, forward or backward. You cannot go backward in time, but you can stand still in space. Inside the event horizon, this flips. The radial direction, the direction pointing toward the center of the black hole, is no longer a direction in space. It is a direction in time. The singularity is not a place you can choose to avoid by steering away from it. It is a moment in your future, as inevitable as tomorrow. You cannot stop moving toward it any more than you can stop moving forward in time. Every possible trajectory you could follow, every action you could take, every thrust of your engines, if you still have engines, only changes when you reach the singularity, not whether you reach it. This is not a metaphor. The mathematics of general relativity inside the event horizon shows that the singularity lies in the future light cone of every event. A light cone is the set of all possible futures that can be reached from a given point in space-time without traveling faster than light. Outside a black hole, your future light cone includes a wide range of locations. You can move in many directions. You have options. Inside the event horizon, every possible future path in your light cone ends at the singularity. There is no path that leads anywhere else. The geometry has closed around you. You are not being pulled toward the singularity by a force. You are moving toward it because it is the only direction time flows. Physicists describe this by saying that the singularity is space-like outside the horizon and time-like inside. Outside, the singularity is a place, a point in space you can avoid by staying far away. Inside, it is a moment, a point in time you cannot avoid because you cannot stop time from passing. The event horizon is the boundary where this transition happens, and once you are on the inside, the rules are different, not slightly different, fundamentally different. The coordinates that describe space-time have shifted their meaning. What used to be spatial coordinates now describe time. What used to be the time coordinate now describes space. The map has rotated, and if you try to navigate using the old map, you will be lost immediately. The second thing to understand is that nobody knows what happens inside, not in detail, not with certainty. General relativity makes predictions, yes, but those predictions are clear about one thing above all else. The theory itself is incomplete. The equations that describe space-time curvature work beautifully outside the event horizon. They predict orbits, gravitational waves, time dilation, all confirmed by observation. Inside the horizon, the equations still run. You can plug in the numbers, you can solve for the geometry. And the geometry you get is disturbing. Space becomes more and more curved as you approach the center. The tidal forces grow without bound. The curvature increases, and at the very center, at the singularity, the curvature becomes infinite. Infinite curvature means the equations have broken. They are giving you an answer that does not make physical sense. Infinity is not a number you can measure. It is a sign that something in the model has failed, that the assumptions you used to derive the equations are no longer valid. General relativity is a classical theory. It treats space-time as smooth and continuous. It does not include quantum mechanics, the framework that describes how matter and energy behave at very small scales. And at the singularity, where all the mass of the black hole is compressed into a region of zero volume, the scales become very small, smaller than atoms, smaller than protons, smaller possibly than anything that has a size in the way we usually think about size. At that scale, quantum mechanics should matter. And when quantum mechanics matters, general relativity stops being a reliable guide. Physicists are honest about this. The singularity, as predicted by general relativity, is probably not real. It is more likely a placeholder, a red flag in the mathematics telling us that a more complete theory is needed. That more complete theory is called quantum gravity, and we do not have it yet. There are candidates. String theory is one. Loop quantum gravity is another. Both attempt to merge quantum mechanics with general relativity, to build a framework that describes space-time at scales where both quantum effects and gravitational effects are strong. But neither theory is complete, neither has been confirmed by experiment, and neither gives a clear, testable prediction about what the interior of a black hole actually contains. So when people ask what is inside a black hole, the most honest answer a physicist can give is this: we do not know. We have models, we have guesses, we have mathematical frameworks that suggest possibilities, but we do not have data. We cannot observe the interior. We cannot send a probe inside and retrieve the measurements. Every signal that crosses the event horizon stays inside. The interior is sealed off from observation, not by technology or distance, but by the structure of space-time itself. We are blind to what happens there, and that blindness is not temporary. It is a consequence of the geometry. The event horizon is a one-way boundary for information. Once information crosses inward, it is gone from the perspective of the outside universe, forever. The classical picture, the one general relativity gives us, is stark. As you fall inward past the event horizon, the tidal forces grow, space stretches. Your body, if it has survived this long, is pulled apart in the radial direction and compressed in the perpendicular directions. Spaghettification continues. The forces increase. At some point, your body is no longer a body. It is a stream of particles falling inward, each particle experiencing its own slightly different trajectory. The stream continues. The tidal forces continue. The particles themselves, atoms, molecules, begin to feel the strain. Atomic bonds break. Electrons are stripped away from nuclei. What is left is a plasma, a hot ionized gas, falling toward the center. Deeper still, the forces exceed the binding energy of atomic nuclei. Protons and neutrons are torn apart into their constituent quarks. The plasma becomes a quark soup, a state of matter that normally only exists in the most extreme environments, inside neutron stars or in particle colliders. The quarks fall inward, the tidal forces grow stronger. And then, according to the classical equations, you reach the singularity, a point of infinite density and zero volume, a place where space-time curvature becomes infinite, where the very notion of distance and time breaks down completely. This prediction is almost certainly wrong. Infinity is not something that appears in physical measurements. It is a signal that the theory has hit a limit. And the limit here is clear. General relativity does not account for quantum mechanics. At the scales where the singularity would exist, quantum effects dominate. The structure of space-time itself, if it even makes sense to talk about structure at that scale, is probably not smooth and continuous the way general relativity assumes. It might be discrete, it might fluctuate, it might be woven from something more fundamental, something that does not look like space and time at all when you zoom in far enough. One possibility, suggested by loop quantum gravity, is that the singularity is replaced by a region of extreme but finite curvature. In this picture, the collapse does not continue to a point of infinite density. Instead, quantum effects generate a kind of pressure that halts the collapse at a very small but non-zero size. The core of the black hole would be incredibly dense, but not infinitely dense. The tidal forces would be enormous, but not infinite. This is called a Planck star, and it is one of several ideas for what might sit at the center of a black hole instead of a singularity. The Planck length, about 10 to the negative 35 meters, is the scale where quantum gravity effects are expected to become important. At that size, space-time itself might have structure, might be grainy or foamy or something else entirely that we do not have good words for yet. Another possibility comes from string theory, which suggests that the fundamental constituents of the universe are not point particles, but tiny loops or strings of energy. In this framework, the singularity might be replaced by a stringy structure, a region where the usual notions of geometry are replaced by something more abstract. The interior of the black hole would still be a region of extreme curvature, but the curvature would be smoothed out at very small scales by the extended structure of the strings. This is speculative. String theory has not made testable predictions about the interior of black holes that we can check against observation, but it provides a mathematical framework where singularities can be avoided, where the breakdown of general relativity is patched by the inclusion of quantum mechanics. A third idea, more radical, is that the interior of a black hole is not a place at all. Some interpretations of quantum mechanics and black hole thermodynamics suggest that all the information about what falls into a black hole is somehow encoded on the event horizon itself, in a kind of holographic projection. The interior, in this view, might not be a separate region of spacetime with its own geometry and matter. It might be an emergent description, a way of organizing the information stored on the horizon. This is the holographic principle, and it has been enormously influential in theoretical physics over the past few decades. But applying it to black holes raises as many questions as it answers. If the interior is holographic, what does it mean to fall in? What are you experiencing if the experience is somehow encoded on a surface you have already crossed? These questions do not have clear answers yet. What all these ideas have in common is that they replace the infinite singularity with something finite, something that does not require infinity, something that could, in principle, be described by a more complete theory. But without experimental data, without a way to test these ideas, they remain speculative. They are educated guesses, built on mathematical frameworks that we think might describe the universe at scales we cannot probe. They are not random guesses. They are constrained by the need to match general relativity in the regimes where general relativity is known to work. But they are guesses nonetheless. One of the frustrating aspects of studying black holes is that the most interesting physics happens in a region we can never observe. If a probe crosses the event horizon and measures the interior, it cannot send the data back. If a signal is emitted from inside the horizon, it falls inward along with everything else. The outside universe loses contact. From the outside, the black hole is simple. It is described by its mass, its spin, and in principle its charge, though astrophysical black holes have negligible charge. That is the no-hair theorem again. All the complexity, all the information about what fell in and what is happening inside is hidden behind the horizon. The black hole looks the same from the outside, whether the interior is a classical singularity or a Planck star or a stringy fuzz or a holographic projection. The horizon hides everything. This informational barrier is part of what makes the black hole information paradox so difficult. If information falls into a black hole and cannot come back out, then information is lost. But quantum mechanics says information cannot be lost. It can be scrambled, spread out, encoded in complicated ways, but it cannot vanish. If black holes destroy information, then quantum mechanics is wrong. If they do not, then general relativity is incomplete in a way that allows information to escape, and we need to understand how. Hawking radiation, The theoretical process by which black holes emit particles due to quantum effects near the horizon might be the answer. The radiation might carry information, but how it encodes that information and whether the encoding is consistent with both quantum mechanics and general relativity is still debated. The paradox is unresolved. It has been unresolved for nearly 50 years, and it will remain unresolved until we have a theory of quantum gravity that works. For the observer falling into the black hole, none of this matters in a practical sense. You are inside. The singularity or whatever replaces it is in your future. You cannot escape. You cannot send a message out. You are isolated. And the physics governing your final moments, the last seconds or minutes before you reach the core, is unknown. General relativity gives a prediction, but it is a prediction that includes infinities, and infinities are not real. Something else happens, something that requires quantum mechanics, something we do not yet understand, and because we cannot observe it, we can only guess. The guessing is not random. It is informed by theory, by mathematics, by consistency with the parts of physics that we do understand, but it is still guessing. We do not have the final theory. We do not have the complete picture. We have pieces. We have frameworks that work in certain limits. We have hints from thought experiments, from calculations, from the internal consistency of the mathematics, but we do not have data. And without data, physics is philosophy. Interesting philosophy, rigorous philosophy, but not science in the sense that we can test it. This is the current state of affairs. The interior of a black hole is a laboratory for quantum gravity, the most extreme laboratory in the universe, and it is a laboratory we cannot access. We can build models, we can solve equations, we can imagine what might be there, but we cannot look. The event horizon is a screen blocking our view. And it is not just that the screen is opaque, it is that the screen is fundamental. It is built into the geometry of space-time. Crossing the screen from the outside requires crossing a boundary where time and space trade roles, where your future becomes locked onto a single destination. And that destination, whatever it is hidden from the rest of the universe by the one-way nature of the horizon. From a purely physical standpoint, the singularity or its replacement is not the most disturbing part. The most disturbing part is that the event horizon seals you off. You can be alive, conscious, recording data, experiencing the interior, and none of it can ever be communicated back. Your experience continues, your proper time keeps ticking, but from the perspective of the outside universe, you have already been lost. Your timeline has diverged. You are in a separate region of space-time, one that is not part of the causal future of anyone outside. You are gone, and everything you see, everything you measure, everything you learn in those final moments dies with you. The black hole keeps its secrets not by encrypting them, but by isolating them behind a geometric barrier that cannot be crossed in the outward direction. This isolation raises questions that go beyond physics into philosophy. If an event happens inside a black hole and no one outside can ever observe it, did it happen in a way that matters to the rest of the universe? The equations say yes, the event happened. Space-time inside the horizon is as real as space-time outside, but the operational answer, the answer from the perspective of what can be measured, is no. The event is sealed off. It does not affect anything outside. It cannot be used to make predictions. It cannot be confirmed. It exists in a region of space-time that is fundamentally separate from the rest. And yet, the black hole itself remains. It has mass. It has spin. It exerts gravity on the space around it. It affects the orbits of nearby stars. It can merge with other black holes, releasing gravitational waves. The interior might be hidden, but the exterior is not. The black hole is a part of the universe. It interacts with the universe. And whatever is inside, whatever replaced the singularity, or whether the singularity is real, the outside sees only the event horizon and the gravitational field. The complexity inside is compressed into a few numbers: mass, spin, charge. That is all the outside can measure. That is all that matters for predicting what the black hole will do next. In some sense, the black hole is a perfect example of the limits of knowledge. There are regions of space-time we can describe mathematically but cannot observe. There are predictions we can make that cannot be tested. There are questions we can ask that might not have answers, not because the answers do not exist, but because the answers are locked behind a boundary that information cannot cross. The event horizon is not just a physical barrier, it is an epistemological one. It divides what can be known from what cannot. And beyond that barrier, in the hidden interior, lies a place where the known laws of physics break down. A place where general relativity admits it cannot describe what is happening. A place where quantum gravity is needed, and quantum gravity does not exist as a complete, tested theory. The interior is a blank spot on the map of physics. We know the blank spot is there. We know it matters. We know that understanding it would teach us something fundamental about how the universe works at its deepest level. But we cannot fill in the blank. We can only draw sketches around the edges, make educated guesses, hope that someday a more complete theory will give us the tools to say with confidence what lies at the center of a black hole. For now, the interior remains unknown, and the journey toward the singularity, or whatever replaces it, remains a one-way trip into a region where space-time itself might not be what we think it is, where the very concepts of distance and time might dissolve into something more fundamental, something we do not yet have the language or the mathematics to describe. You cross the horizon, you fall inward, the tidal forces grow, and then, in your final moments, you reach the core. What happens there, no one knows. The equations predict infinity. Infinity is wrong. Something else happens, something finite, something real, but the universe outside will never know what it was. This is where general relativity stops and quantum gravity begins. This is where the very large, the black hole, meets the very small, the quantum scale. This is where the map ends and the unknown begins. And just beyond that unknown, in the speculative fringes of theoretical physics, lies a question even stranger than what is inside. If there is a way in, is there a way out? Not from this black hole, not from this event horizon, but from something else. Something that might exist as the mirror image of a black hole, the time-reversed twin, the exit to a tunnel that no one has ever seen, a white hole. And that idea, as strange as it sounds, is where the next part of this story goes. You cross the horizon, you fall inward, the tidal forces grow, and then, in your final moments, you reach the core. What happens there, no one knows. The equations predict infinity. Infinity is wrong. Something else happens, something finite, something real. But the universe outside will never know what it was. The event horizon is a one-way door. It swings inward, it locks behind you. And according to every calculation, every simulation, every line of math we have used to describe black holes for more than a century, that door does not swing the other way. There is no exit, there is no back door, there is no secret passage leading out, unless there is. The idea sounds absurd at first. A black hole is defined by the fact that nothing escapes. The event horizon is the boundary where escape velocity exceeds the speed of light. Once you cross it, every possible future trajectory leads inward. The geometry of space-time itself has closed around you. There is no outward direction left. That is the defining feature of a black hole. So the notion that there could be something else, something opposite, something that behaves like a black hole running backward in time, feels like a joke, a mathematical trick, a solution to an equation that describes nothing real. It is called a white hole, and it is exactly that. A mathematical trick, a solution to the same equations that describe black holes, but with time reversed. Where a black hole is a region you can enter but never leave, a white hole is a region you can leave but never enter. Light and matter pour out of a white hole. They emerge from an event horizon, not into one. The horizon is still a one-way boundary, but the direction is flipped. Inside is sealed off, not from the future, but from the past. You cannot fall into a white hole. You cannot approach it. You cannot send a signal into it. You can only watch things come out of it, endlessly, as if the white hole is vomiting matter and energy into the universe from some hidden reservoir that you can never access. This is not science fiction. This is general relativity. The mathematics that describes black holes, the Schwarzschild solution to Einstein's field equations, has a time-reversed twin. Flip the sign on the time coordinate and the solution still works. The geometry is still valid. The equations are still satisfied. What you get is a white hole, same mass, same spin if you include rotation, same event horizon radius, same singularity at the center. The only difference is the direction. A black hole pulls everything in. A white hole pushes everything out. Both are solutions to the same equation. Both are, in a purely mathematical sense, allowed by the theory. And yet, no one has ever seen one. Not once. Not a hint. Not a candidate. Not a distant object in some galaxy billions of light years away that behaves even remotely like what a white hole should behave like. The universe is full of black holes. We have found thousands of them. We have imaged their event horizons. We have detected the gravitational waves from their collisions. We have tracked stars orbiting them. We have measured their masses, their spins, their effects on nearby gas and dust. Black holes are real. They are confirmed. They are part of the standard astrophysical toolkit. White holes are not. White holes are a footnote, a curiosity, a thing that shows up in textbooks as an example of how general relativity permits solutions that do not correspond to anything in the physical universe. The reason is simple. There is no way to make one. Black holes form from gravitational collapse. A massive star runs out of fuel. The core implodes. If the core is heavy enough, nothing stops the collapse, and a black hole forms. The process is violent, messy, chaotic, but it is a process. It happens. Stars collapse. Black holes appear. We have watched it happen, or at least watched the aftermath. Supernova remnants, X-ray binaries, quasars, all of them trace back to black holes formed by collapse. The formation mechanism is known. It is testable. It is part of the life cycle of massive stars. White holes have no formation mechanism. There is no known process in nature that creates a region of space-time from which matter can only escape. You cannot reverse a gravitational collapse and get a white hole. If you tried to run a black hole backward in time, you would get an explosion, a star uncollapsing, matter flying outward. But that is not a white hole. That is just a movie of a supernova played in reverse. A white hole is not an explosion. It is a persistent object, a region with an event horizon, a singularity at the center, a geometry that looks like a black hole, but with time flipped. To make one, you would need to start with a singularity that already exists and let it expel matter. But singularities do not just appear. They form from collapse. And once they form, they are inside black holes, not white holes. Some physicists have speculated that white holes could have formed in the early universe. in the chaotic conditions right after the Big Bang. The idea is that the universe at its very beginning was so dense, so hot, so far from equilibrium, that local regions could have collapsed into black holes, while other regions, by some symmetry or quantum fluctuation, could have formed white holes. This is not impossible. The early universe was strange. Space-time itself was being created, stretched, curved by the expansion. If white holes were going to form anywhere, it would have been then. But there is no evidence for this. No observations, no signals, no relics. If white holes formed in the early universe, they either decayed, evaporated, or are so rare that we have not found one yet, despite decades of searching. Another idea, more speculative, comes from loop quantum gravity, one of the candidate theories for quantum gravity. In this framework, the singularity at the center of a black hole is not a point of infinite density. It is replaced by a region of extreme but finite curvature, a kind of quantum bounce. Some researchers working in loop quantum gravity have suggested that this bounce could, in principle, convert a black hole into a white hole. The idea is that matter falls into the black hole, reaches the core where quantum effects dominate, bounces, and then re-emerges as a white hole on the other side. This process would take an enormous amount of time from the perspective of an outside observer due to time dilation. The black hole would sit there, looking like a black hole for billions or trillions of years. Then, eventually, it would flip. It would become a white hole. Matter would start pouring out. The event horizon would reverse. This is deeply speculative. It is not part of mainstream physics. It is an idea that falls out of one particular approach to quantum gravity, and even within that approach, the details are murky and the predictions are hard to test. The timescale for the transition, if it happens at all, is so long that no white hole formed this way would have appeared yet in the history of the universe. They would all still be black holes waiting to flip. And when they do flip, the signal they produce might be so faint or so brief that we would miss it unless we were looking in exactly the right place at exactly the right time. The idea is interesting. It is mathematically rich, but it is not something you can point a telescope at and confirm. The lack of evidence is damning. If white holes existed in any significant number, we should see them. They would shine. Not in the way stars shine, but in the way that matter and energy pouring out of a region of space-time would produce detectable signals. Light streaming out of a white hole event horizon would be blue shifted, the opposite of the redshift you see near a black hole. The frequency would increase. The energy would be higher. If white holes were out there, feeding energy into the universe, we should see bright, compact sources that do not match any known astrophysical process. We do not. The universe is full of bright, compact sources. We call them quasars, gamma-ray bursts, supernovae, active galactic nuclei. Every single one of them has been explained by processes that do not require white holes. Black holes, yes. White holes, no. Some researchers have tried to link white holes to the Big Bang itself. The idea is that the Big Bang, the moment when the universe began, looks a lot like a white hole if you squint at the math the right way. The Big Bang was a moment when everything in the universe emerged from a singularity. Space expanded, matter and energy poured outward. That sounds like a white hole, a region from which everything escapes and nothing enters. The analogy is appealing, and it shows up in popular science discussions fairly often, but it is not quite right. The Big Bang was not a localized event. It did not happen at a point in space. It happened everywhere. The entire universe was the singularity, or more accurately, the universe emerged from a state of extreme density and temperature that we call the Big Bang. A white hole, by contrast, is a localized object sitting in an already existing spacetime. It has a boundary, an event horizon, a region outside where space is normal, and a region inside where space is sealed off. The Big Bang does not have that structure. The comparison breaks down when you look closely. There is another version of the idea called the fountain model. In this picture, the universe is not just expanding from a Big Bang. It is being fed by white holes scattered throughout spacetime, continuously injecting matter and energy into the cosmos. The universe becomes a kind of Xinquan system, where black holes swallow matter on one end and white holes eject it on the other. The idea has a certain elegance. It balances inflow and outflow. It avoids the need for a single moment of creation, but it has problems. Where are the white holes? What connects them to the black holes? How does matter get from one to the other? The fountain model does not answer these questions in a way that matches observations. The universe we see is not in equilibrium. It is expanding. It is cooling. The matter distribution is not uniform. Galaxies are not evenly fed by fountains. The model does not fit the data. Sean Carroll, a theoretical physicist at Caltech, has been quoted saying that a black hole is a place where you can go in but you can never escape, and a white hole is a place where you can leave but you can never go back. He notes that otherwise the two share exactly the same mathematics, exactly the same geometry. That is the core of the issue. The math allows white holes. The geometry is valid. The equations do not forbid them. But the universe does not seem to care what the equations allow. The universe is under no obligation to realize every possible solution to every equation. General relativity permits white holes. Nature apparently does not. This is not unusual in physics. There are many solutions to equations that describe things that do not exist. You can write down a solution to Maxwell's equations that describes a magnetic monopole, a particle with only a north pole or only a south pole. The math works, the solution is clean, but magnetic monopoles have never been found. They might not exist. The equations allow them, but the universe does not seem to produce them, at least not in any form we can detect. White holes are similar. They are mathematically allowed, physically absent. One reason white holes are considered non-physical is stability. Even if you could somehow create a white hole, it would not last. General relativity says that white holes are unstable in a way that black holes are not. A black hole is stable because everything that approaches it falls in. Perturbations, small disturbances in the surrounding spacetime, get swallowed. They do not disrupt the black hole, they just add to its mass. A white hole is the opposite. Perturbations cannot fall in. They bounce off the event horizon, or more accurately, they cannot even approach the horizon because the geometry forbids inward motion. But that means any small disturbance in the environment around a white hole would build up, reflect, interfere with the outgoing flow of matter and energy. The white hole would not be able to maintain its structure. It would destabilize. Some calculations suggest that even a single photon approaching a white hole from the outside would be enough to disrupt it, causing the event horizon to collapse or the geometry to break down. If that is true, then white holes, even if they could form, would be destroyed almost immediately by the ambient radiation and matter in the universe. They would flicker into existence and vanish. We would never see one because they would never last long enough to be seen. This instability is not shared by black holes. Black holes are robust. You can throw matter at them, energy, radiation, whatever you like, and they just absorb it. They grow, they stabilize, they persist. White holes do not have that luxury. The one-way nature of their event horizon, which prevents anything from entering, also prevents them from interacting with their environment in a way that maintains equilibrium. They are fragile. And fragile objects do not survive in a universe full of photons, neutrinos, cosmic rays, and wandering hydrogen atoms. Another issue is the arrow of time. The universe has a direction. Entropy increases. Systems move from order to disorder. The second law of thermodynamics is not just a suggestion. It is one of the most robust principles in all of physics. Black holes fit into this framework. They increase entropy. When matter falls into a black hole, the entropy of the universe goes up. Stephen Hawking and Jacob Bekenstein showed in the 1970s that black holes have entropy proportional to the area of their event horizons. The more massive the black hole, the higher the entropy. The universe, by forming black holes, is moving in the direction of higher entropy, which is the direction the second law says it should move. White holes do not fit. A white hole expelling matter into the universe would be decreasing entropy locally. It would be taking a region of high entropy, the interior, and spreading it into a region of lower entropy, the exterior, that runs backward. It violates the arrow of time in a way that makes physicists uncomfortable. You can argue that the total entropy of the universe, including the white hole, still increases, but the details are tricky. The thermodynamics of white holes are not well understood because white holes are not well understood. And the fact that they seem to run counter to the natural flow of time is another reason most cosmologists dismiss them as non-physical. There is also the question of what you would see if you somehow encountered a white hole, not from the inside, because you cannot get inside. The event horizon forbids entry, but from the outside, watching it. What would it look like? The answer depends on the details, but the rough picture is this. You would see matter and light streaming out of a region of space. The light would be blue-shifted because it is climbing out of a gravitational well in the opposite direction from normal. The energy would be high. The brightness would be intense. The outflow would be continuous, or at least persistent, assuming the white hole is not immediately destroyed by instabilities. It would look, in some ways, like an explosion, but not a normal explosion. Explosions fade. They dissipate. A white hole would keep going, pouring energy into the universe from a source you cannot access or explain. Astronomers have looked for objects like this. Gamma-ray bursts, for example, are brief, intense flashes of high-energy light that appear randomly across the sky. Some of them are so bright that they outshine entire galaxies for a few seconds. They have been explained by other mechanisms: collapsing stars, colliding neutron stars, jets from black holes. But early on, before those explanations were confirmed, some researchers suggested that gamma-ray bursts could be white holes. Brief, intense, energetic, appearing out of nowhere. The idea did not hold up. Gamma-ray bursts have features, afterglows, host galaxies, spectra that match the standard explanations. They do not need white holes. And once you have a simpler explanation that fits the data, the more exotic idea gets discarded. That is how science works. You do not invoke white holes unless you have to, and so far we have not had to. There is a version of the white hole idea that is less extreme and slightly more plausible, though still speculative. It involves wormholes. A wormhole is a tunnel through space-time, a shortcut connecting two distant regions. The math that describes wormholes is related to the math that describes black holes and white holes. In fact, the original solution to Einstein's equations that describes a black hole, the Schwarzschild solution, includes a wormhole connecting the black hole to a white hole. The geometry is called the Schwarzschild wormhole, or sometimes the Einstein-Rosen bridge, after the physicists who explored it in the 1930s. In this geometry, the black hole and the white hole are two ends of the same tunnel. Matter falls into the black hole. It travels through the tunnel. It emerges from the white hole. This sounds like a neat solution. It avoids the singularity. It provides an exit. It makes white holes useful. The problem is that the Schwarzschild wormhole does not stay open. The geometry is unstable. The tunnel collapses before anything can pass through it. To keep a wormhole open, you need something called exotic matter, a type of matter with negative energy density. Exotic matter has never been observed. It might not exist. And even if it does, there is no known way to collect enough of it to stabilize a wormhole large enough for anything useful to pass through. The wormhole, if it formed at all, would collapse in a fraction of a second. Anything trying to travel through it would be crushed. The connection between the black hole and the white hole would be severed, and you would be left with two separate objects. One, an entrance with no exit, the other, an exit with no entrance, neither of which connects to the other in any meaningful way. This brings us to the edge of what general relativity can tell us. The theory allows white holes. It allows wormholes. It allows a number of exotic geometries that do not seem to correspond to anything real. The theory is extraordinarily successful at describing the universe we see, but it does not force the universe to realize every solution. Some solutions are unstable. Some require conditions that do not occur in nature. Some are artifacts of the mathematics, features of the coordinate system, or the symmetry of the problem that do not survive when you add more realistic details. White holes fall into this category. They are a consequence of the time symmetry in the equations, but the universe is not time symmetric. It has an arrow. It has a direction, and that direction points away from white holes and toward black holes. Most cosmologists, when pressed, will say that white holes are almost certainly not real. They are a mathematical exercise with no real-world counterpart. They are interesting to think about, useful for teaching students about the structure of space-time and the symmetries of general relativity, but not something you should expect to find. The universe does not build them. It does not sustain them. It does not need them. Black holes are enough. Black holes do the job of concentrating mass, storing entropy, anchoring galaxies, shaping the large-scale structure of the cosmos. White holes add nothing to this picture except confusion. And yet, the idea persists. It shows up in popular science articles. It shows up in speculative papers on quantum gravity. It shows up in discussions about the Big Bang, the ultimate fate of black holes, the possibility of other universes connected to ours through bridges we cannot see. The idea persists because the math is clean, because the symmetry is elegant, because the notion of an exit is appealing in a universe where black holes represent the ultimate dead end. We want there to be a way out. We want the one-way doors to have a back exit. We want the geometry to be fair, to balance every entrance with an exit, every black hole with a white hole. But wanting is not enough. The universe does not care what we want. It cares about what is stable, what is probable, what emerges from the messy, chaotic, asymmetric process of cosmic evolution. And in that process, white holes do not seem to appear. So we are left with a footnote, a theoretical possibility, a solution to an equation that describes a thing that probably does not exist. White holes remain hypothetical. They remain unobserved. They remain, for now, a curiosity at the edges of general relativity, a reminder that the equations permit more than the universe delivers. And if white holes are the theoretical exits, tantalizing in their symmetry but absent in reality, then wormholes are the theoretical shortcuts, the tunnels that might connect distant parts of the universe or even separate universes entirely. They share the same mathematical roots as white holes. They rely on the same exotic geometries, and they raise the same uncomfortable question. Just because the math allows something, does that mean it can exist? Or are we chasing shadows, solutions to equations that describe nothing more than the limits of the theory itself? Wormholes are everywhere in science fiction. Starships use them to cross the galaxy in minutes. Heroes dive through them to escape danger or explore parallel universes. They are presented as shortcuts, cosmic tunnels that fold space like a piece of paper, allowing you to poke a hole through and step from one side to the other without traveling the distance in between. The idea is compelling, the visuals are dramatic, and the physics, at least on the surface, seems to allow it. General relativity, the same theory that gave us black holes and predicted gravitational waves and explained the bending of light around massive objects, also permits solutions that look like tunnels through space-time. These solutions are called wormholes. The term itself was coined in 1957 by physicist John Wheeler, though the concept goes back further. Wheeler imagined space-time as a kind of foam at very small scales, riddled with tiny fluctuating wormholes connecting different points. The name stuck, and the idea, once it entered popular culture, never left. The mathematical foundation for wormholes comes from the same place as black holes. In 1916, just months after Einstein published the general theory of relativity, a German physicist named Karl Schwarzschild derived a solution to Einstein's equations that describes the spacetime around a spherical, non-rotating mass. This is the Schwarzschild solution, and it is still the starting point for almost every discussion of black holes. But buried in the Schwarzschild solution is something strange. The geometry does not just describe a black hole sitting in empty space. It describes a black hole connected to another region of space-time through a kind of bridge. One side of the bridge is the black hole, where things can enter but not leave. The other side is a white hole, where things can leave but not enter. And connecting the two is a throat, a tunnel, a passage through the curved fabric of space-time itself. This structure is called the Einstein-Rosen bridge, named after Einstein and his collaborator Nathan Rosen, who explored the idea in a 1935 paper. On paper, it looks like a wormhole. It connects two regions of space-time. It provides a path from one to the other. The problem is that the Einstein-Rosen bridge does not work the way science fiction wormholes are supposed to work. It is not traversable. The throat of the bridge, the tunnel connecting the black hole to the white hole, collapses faster than light can cross it. If you tried to travel through an Einstein-Rosen bridge, you would not make it. The geometry would pinch off before you reached the other side. You would be crushed, or more accurately, you would be trapped in a collapsing region of space-time with no exit. The bridge exists in the math, yes, but it exists for such a short time, measured in the geometry's own internal clock, that nothing can use it. It is a tunnel that seals itself shut the moment it opens. This is the critical distinction that most popular treatments of wormholes gloss over. The original wormhole solution, the one that falls naturally out of general relativity, is not a shortcut. It is a dead end. You cannot travel through it. You cannot use it to hop from one part of the universe to another. It connects a black hole to a white hole, and we have already established that white holes probably do not exist. Even if they did, the connection would be severed before you could exploit it. The Einstein-Rosen bridge is a mathematical curiosity, not a transportation system. It tells us something interesting about the structure of space-time, about the kinds of geometries general relativity allows, but it does not give us a way to cross the galaxy in an afternoon. So if the Einstein-Rosen bridge does not work, what would? The question was taken up seriously in the 1980s by physicists Kip Thorne, Michael Morris, and Ulvi Yurtsever. Thorne, who would later win the Nobel Prize for his work on gravitational waves, was interested in whether you could construct a wormhole that stays open long enough for something or someone to pass through. Not a naturally occurring wormhole, which seemed unlikely, but a hypothetical wormhole that could be built if you had the right materials and the right understanding of the physics. The team worked out the requirements. What they found was not encouraging. To keep a wormhole open, you need something called exotic matter. Not exotic in the sense of rare or unusual, exotic in the sense of violating the normal rules. Exotic matter is matter with negative energy density. Every type of matter we have ever encountered has positive energy density. Atoms have mass, photons have energy. Even the vacuum of space, according to quantum field theory, has a small positive energy density associated with virtual particles popping in and out of existence. Positive energy density curves space in a way that pulls things together. It creates gravity. It attracts. Negative energy density would do the opposite. It would curve space in a way that pushes things apart. It would create a kind of anti-gravity. And if you could line the throat of a wormhole with exotic matter, the repulsive effect would hold the throat open, preventing it from collapsing. The problem is that exotic matter, as far as we know, does not exist. There are hints in quantum mechanics that something like it might be possible under very specific conditions. The Casimir effect, for example, involves two metal plates placed very close together in a vacuum. Quantum fluctuations in the space between the plates create a pressure difference that pushes the plates together. The energy density between the plates is slightly lower than the energy density outside, which can be interpreted with some mathematical maneuvering as a region of negative energy. But the effect is tiny. The energy involved is minuscule. And there is no known way to scale it up to the levels required to stabilize a wormhole large enough for anything macroscopic to pass through. The amount of exotic matter you would need, according to most estimates, would be enormous. Some calculations suggest you would need more negative energy than the total positive energy in several stars. That is not a small engineering challenge. That is a request for something that might be fundamentally impossible. Even if you could gather the exotic matter, you would face another problem: stability. Wormholes, even the traversable kind that exotic matter is supposed to hold open, are fragile. They are sensitive to perturbations. A single particle passing through the wormhole can disturb the geometry. The disturbance propagates. The throat wobbles. The structure destabilizes. Some studies suggest that even the passage of light through a wormhole could be enough to trigger a collapse. The photons carry energy. The energy affects the curvature. The curvature changes the shape of the throat. And once the throat starts to change, the feedback can be catastrophic. The wormhole pinches shut, trapping or destroying whatever is inside. This is not a minor technical hurdle. This is the geometry itself fighting back against the idea of a stable tunnel. Thorne and his collaborators were aware of these issues. Their work in the 1980s was not a proposal to build a wormhole. It was an exploration of what the laws of physics would require if a wormhole were to exist. They were asking, in effect, what would it take? And the answer they got was, a lot. More than we have. Possibly more than the universe allows. The papers were rigorous. The math was solid. And the conclusion, read between the lines, was that traversable wormholes are almost certainly not something you can build in the real world. They remain, like white holes, a solution to an equation that does not correspond to anything nature produces. This has not stopped people from speculating. If wormholes could exist, they would have extraordinary properties. One of the most talked about is their potential use as time machines. The idea goes like this. Imagine you have a wormhole with two mouths, two openings, sitting next to each other in space. You take one mouth and accelerate it to a significant fraction of the speed of light, then bring it back. Due to time dilation, a consequence of special relativity, the moving mouth ages more slowly than the stationary mouth. When you bring it back, the two mouths are no longer synchronized in time. One mouth is in the present, the other is in the past. Or more accurately, one mouth is slightly behind the other. If you step through the mouth that moved, you emerge from the other mouth at an earlier time. You have traveled backward in time. Not far, maybe just a few hours or days depending on how fast you moved the mouth and for how long, but backward nonetheless. This is not a trick. This is a prediction that falls out of combining general relativity with special relativity. If wormholes exist, and if you can move one mouth relative to the other, then you can create a time machine. The implications are staggering. Time travel into the past opens the door to paradoxes. The classic example is the grandfather paradox. You travel back in time and prevent your grandfather from meeting your grandmother. You are never born, but if you are never born, you cannot travel back in time to prevent the meeting. The loop closes on itself. The logic breaks. Physicists have spent decades arguing about whether such paradoxes are a sign that time travel is impossible, or whether the universe has some mechanism, some consistency condition that prevents paradoxes from occurring even if time travel is allowed. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time machines from forming. The conjecture is not proven, it is a guess, an educated guess based on the discomfort physicists feel when confronted with paradoxes. But it is not a law, it is not settled. The more immediate issue is that creating a time machine out of a wormhole requires you to have a wormhole in the first place, and we do not. We have never seen one. We have never detected one. We have no evidence that they exist anywhere in the universe. Astronomers have looked. If a wormhole were sitting in space, it would have observable effects. It would lens light, bending the paths of photons that pass near it, just like a black hole does. The lensing pattern would be different, potentially distinguishable if you looked closely enough, but no such pattern has been found. Surveys of the sky, searches for unusual gravitational lensing events have turned up nothing that looks like a wormhole. They have found black holes, they have found neutron stars, they have found galaxies, quasars, clusters, all the usual suspects, but no wormholes. Some researchers have proposed that wormholes could be hiding in the data, masquerading as black holes. The idea is that a wormhole and a black hole might look similar from the outside, both producing strong gravitational fields, both bending light in comparable ways. If you were far away and you did not have detailed measurements, you might mistake one for the other. But the differences should show up in precision observations. A black hole has an event horizon, a one-way boundary. A wormhole does not. A wormhole has a throat that connects to another region of space, and matter or light entering the throat would not be trapped. It would pass through. That should produce signals, light curves, accretion patterns that differ from what a black hole would produce. No such signals have been detected. The objects we identify as black holes behave like black holes, not wormholes. The simplest explanation is that they are black holes. Wormholes remain theoretical. There is also the question of where a wormhole would come from if it existed. Black holes form from gravitational collapse. We know the process. We have observed the stages. We can point to a massive star, watch it explode, and identify the black hole left behind. Wormholes do not have an equivalent formation mechanism. You cannot collapse a star into a wormhole. The geometry does not work that way. The natural endpoint of gravitational collapse is a singularity, and the singularity is hidden inside an event horizon. It is a black hole, not a wormhole. To get a wormhole, you would need to start with a different set of conditions that general relativity does not obviously provide. One possibility, speculative and untestable at present, is that wormholes could have formed in the very early universe. The moments after the Big Bang were chaotic. The energy densities were extreme. Space-time itself was being stretched and shaped by the expansion. In that environment, quantum fluctuations could have produced all sorts of exotic structures, including, perhaps, tiny wormholes. These primordial wormholes, if they formed, would have been microscopic, far smaller than an atom. Most of them would have evaporated almost immediately due to quantum effects, but some researchers have speculated that a few might have survived, grown, or been stabilized by unknown processes. If any primordial wormholes still exist, they would be incredibly rare, incredibly small, and incredibly difficult to detect. Searching for them is like searching for a needle in a cosmic haystack, except the needle might not exist, and the haystack is the entire observable universe. Kip Thorne, whose work on traversable wormholes in the 1980s helped make the concept scientifically respectable, has been careful to emphasize the hypothetical nature of the idea. He worked as a consultant on the film Interstellar, which features a wormhole prominently in its plot. The wormhole in the film was designed to be as scientifically accurate as possible within the constraints of the story. It was depicted as a sphere, not a flat disk, because that is what a three-dimensional tunnel through space-time would look like when viewed from the outside. The visual effects team used equations from general relativity to simulate how light would bend around the wormhole, creating a distorted view of the space on the other side. The result was one of the most scientifically grounded depictions of a wormhole ever put on screen. But even Thorne would tell you that the wormhole in Interstellar is fiction. It is based on real physics, yes, but it requires exotic matter to stay open, and exotic matter is not something we have lying around. The movie does not explain where the wormhole came from or how it was stabilized. It just posits that it exists, placed there by an advanced civilization, and uses that as a narrative device. That is fine for storytelling. It is not a roadmap for engineering. The energy requirements are another staggering obstacle. Even if exotic matter exists, even if you could figure out how to collect it, or create it, or manipulate it, the amount of energy needed to construct and maintain a wormhole would be astronomical. Some estimates suggest you would need energy equivalent to the mass energy of several stars, converted entirely into the exotic matter required to line the throat. The mass energy of the Sun, using Einstein's equation E equals mc squared, is about 2 × 10⁻47 joules. That is more energy than humanity has generated in its entire history by a factor of trillions. And you would need several times that much, in a form of matter that probably does not exist, to build a wormhole large enough for a person to pass through. The engineering is not just difficult, it is absurd, and yet the idea persists. Wormholes show up in theoretical papers, in discussions about quantum gravity, in speculations about the structure of space-time at the smallest scales. Some versions of string theory, a candidate for a theory of quantum gravity, suggest that space-time might be laced with tiny wormholes at the Planck scale, lengths of about 10⁻⁻35 meters. These wormholes would not be traversable. They would be quantum foam, fluctuating in and out of existence, connecting points in space-time in a constantly shifting web. They would have no macroscopic consequences. You could not use them to travel. You could not even detect them directly. But their existence, if string theory is correct, would tell us something fundamental about the fabric of reality. Space-time, at its deepest level, might not be smooth. It might be stitched together from something more fundamental, threaded with connections that blur the distinction between here and there. This is all deeply speculative. String theory has not been confirmed. The Planck scale is so small that we have no way to probe it with current technology. The wormholes, if they exist at all, are entirely theoretical. And even if they are real, they do not provide a shortcut across the galaxy. They are quantum artifacts, not cosmic highways. The wormholes of science fiction, the ones large enough to fly a spaceship through, remain firmly in the realm of imagination. Stephen Hurst, a theoretical physicist, was quoted in a report saying that the whole thing is very hypothetical at this point. That is putting it mildly. Wormholes are hypothetical in the sense that they are allowed by the equations of general relativity, but they are unsupported by any observational evidence, unconfirmed by any experiment, and plagued by stability problems, exotic matter requirements, and energy costs that border on the impossible. They are mathematically interesting. They are useful for teaching students about the flexibility of space-time geometry. They are fun to think about, but they are not real in any sense that matters for practical purposes. The Britannica summary of wormholes makes the point plainly. Wormholes are intrinsically unstable. Proposed stabilization schemes have no evidence of working. The consensus in the physics community is that traversable wormholes, if they are possible at all, require conditions so extreme and so unlikely that nature probably never produces them. They are a feature of the math, not a feature of the universe, and the distinction matters. Just because general relativity permits a solution does not mean the universe is obligated to realize it. The equations allow white holes. The universe does not build them. The equations allow traversable wormholes. The universe, as far as we can tell, does not build those either. This does not stop wormholes from being useful as thought experiments. They let physicists explore the limits of general relativity. They force us to confront questions about time travel, causality, the nature of space-time. They test the boundaries of what the theory allows and where it breaks down. In that sense, wormholes have been enormously productive, even if they never lead to a working prototype. The conversations they spark, the papers they generate, the debates they fuel, all of that contributes to our understanding of the universe, even if the conclusion is that wormholes are not real. And that, for now, is where we are. Wormholes remain a solution in search of a problem. They are cosmic shortcuts that probably do not exist. They are bridges that probably cannot be built. They are time machines that probably violate the rules. The math says maybe, the universe says no. And until someone finds evidence to the contrary, evidence in the form of an actual observed wormhole, or a confirmed source of exotic matter, or a new theory that changes the game entirely, wormholes will remain what they have always been: a beautiful idea, a tantalizing possibility, a fantasy wrapped in equations, science fiction dressed up as science, and in the end, that might be all they ever are. But if wormholes are the dream of shortcuts through space, black holes are the reality of deep distortions in the fabric itself. They are not portals, they are not tunnels. They are wounds in space-time, scars left by collapsed stars, anchors holding galaxies together, engines driving some of the most violent processes in the cosmos. And their influence reaches far beyond the immediate neighborhood of their event horizons. Black holes shape the universe. They sculpt the distribution of matter. They regulate star formation. They carve channels through the cosmic web. They are not passive objects sitting quietly in the dark. They are active participants in the evolution of the cosmos, and their unseen influence is written into the structure of everything around us. This is where the story stops being about what black holes are and starts being about what they do. Not just to the unfortunate matter that falls into them, not just to the stars orbiting nearby, but to entire galaxies, to the large-scale structure of the universe. To our understanding of how physics works at the deepest level, black holes are not footnotes in the history of the cosmos, they are architects. And the blueprints they are working from have been shaping the universe for billions of years. Start with galaxies. Every large galaxy we have ever surveyed contains a supermassive black hole at its center. Not most galaxies, not some galaxies, every large galaxy. The Milky Way has Sagittarius A star, weighing 4 million times the mass of the Sun. Andromeda has one that weighs roughly 140 million solar masses. Messier 87, the giant elliptical galaxy that gave us the first direct image of a black hole, has one weighing 6.5 billion times the Sun. These are not rare objects sitting at the fringes of astrophysics. They are central features, literally. They sit at the gravitational centers of their galaxies, and they have been there for most of the galaxy's history. The relationship between a supermassive black hole and its host galaxy is not accidental. Observations over the past few decades have revealed a tight correlation between the mass of the central black hole and the properties of the galaxy around it. Specifically, the mass of the black hole correlates with the mass of the galactic bulge, the dense spherical region of old stars surrounding the center. Bigger bulge, bigger black hole, the ratio is remarkably consistent. Across galaxies of wildly different sizes and types, the central black hole weighs about 0.5% of the bulge mass. That precision is not a coincidence. It is a sign that the black hole and the galaxy grew together, that they influenced each other, that their histories are intertwined. How does a black hole weighing a few million or a few billion solar masses influence a galaxy containing hundreds of billions of stars? The answer is energy. Black holes are among the most efficient engines in the universe at converting matter into energy. When gas falls toward a black hole, it heats up. Friction in the accretion disk, the swirling ring of doomed material orbiting just outside the event horizon, generates temperatures of millions of degrees. At those temperatures, the gas radiates across the spectrum. X-rays, ultraviolet light, visible light, all pouring outward from a region that can be smaller than our solar system. The luminosity can exceed the combined light of every star in the galaxy. That is a quasar, a supermassive black hole feeding actively, outshining its host. But the light is only part of the story. The energy pouring out of an active black hole does not just escape into space. It slams into the surrounding gas. It heats the interstellar medium, the diffuse material between stars. It drives winds, powerful outflows of gas, moving at thousands of kilometers per second. It launches jets, narrow beams of plasma that can extend for hundreds of thousands of light years, punching through the galaxy and spraying energy into the intergalactic medium beyond. These jets are some of the most dramatic structures in astrophysics. They are powered by the spin of the black hole and the magnetic fields threading the accretion disk, and they carry so much energy that they can reshape the entire environment around a galaxy. This process is called feedback. The black hole eats gas. The gas heats up and radiates energy. The energy pushes on the surrounding material, heating it, disrupting it, preventing it from collapsing into new stars. Star formation depends on cold gas. If the gas is too hot, it cannot collapse. The pressure is too high. The clouds disperse instead of condensing. By heating the gas, the black hole shuts down star formation in the central regions of the galaxy. The feedback loop is self-regulating. The black hole grows by eating gas, but the act of eating releases energy that drives away the remaining gas, starving the black hole. The feeding slows, the energy output drops, the gas cools, star formation resumes, more gas drifts inward, the black hole wakes up, and the cycle repeats. This feedback is not a minor effect, it is one of the dominant processes shaping galaxy evolution. Simulations of galaxy formation that do not include black hole feedback produce galaxies that look nothing like the ones we observe. They make galaxies that are too massive, with too many stars, with star formation rates that are far too high. Add black hole feedback to the simulations, and the results match reality much more closely. The galaxies stop growing at the right size. The star formation rates drop to observed levels. The central regions develop the old red stellar populations we see in real galaxies. The black hole, despite being a tiny fraction of the galaxy's total mass, controls the growth of the entire system. The mechanism is not fully understood. The details are messy. The feedback depends on the mass of the black hole, the rate at which it is accreting gas, the strength of the magnetic fields, the density and temperature of the surrounding medium, the history of previous outbursts. Every galaxy is different. Every black hole has its own story, but the overall pattern is clear. Black holes regulate galaxies. They prevent runaway growth. They shape the distribution of gas and stars. They are not passengers, they are drivers. This has implications for the structure of the universe on the largest scales. Galaxies are not scattered randomly through space, they cluster. They form groups, clusters, superclusters, connected by filaments of dark matter and gas in a vast cosmic web. The nodes of the web, the places where the filaments intersect, are where the largest galaxy clusters sit. And at the centers of those clusters, in the most massive galaxies, sit the most massive black holes, billions of times the mass of the Sun. These are the giants, and their feedback extends beyond their host galaxies. The energy they pump into the intracluster medium, the hot gas filling the space between galaxies in a cluster, can heat that gas to tens of millions of degrees. That heat prevents the gas from cooling and falling into the galaxies to form stars. Without black hole feedback, galaxy clusters would be much brighter in X-rays, much richer in star formation, much more active than they are. Black holes keep the clusters in check. One of the clearest examples of this is the Perseus cluster, a massive collection of over 1,000 galaxies sitting about 250 million light-years from Earth. At the center of the cluster is a giant elliptical galaxy called NGC 1275. At the center of that galaxy is a supermassive black hole, and surrounding the galaxy, visible in X-ray images, are enormous cavities in the hot intracluster gas. Bubbles, voids, regions where the gas has been pushed aside by jets from the central black hole. The bubbles are tens of thousands of light-years across. They contain enough energy to power the Sun for trillions of years. The black hole has been inflating these bubbles for millions of years, pushing against the surrounding gas, preventing it from collapsing. The feedback is not hypothetical. It is right there in the data. You can see the cavities. You can measure their size. You can calculate the energy. The black hole is sculpting the cluster. This is happening everywhere, not just in Perseus. In every massive galaxy cluster, the central black hole is active, or has been active in the recent past, and the fingerprints of that activity are visible in the structure of the surrounding gas. The universe, at large scales, is being shaped by black holes. Their influence extends far beyond the event horizons, far beyond the accretion disks, far beyond the galaxies themselves. They are cosmic thermostats, regulating the temperature and density of the gas that fills the space between galaxies, controlling where and when stars can form, shaping the evolution of the largest structures in the universe. And they do all of this while remaining, for the most part, invisible. We do not see the black holes, we see their effects. We see the jets, we see the heated gas, we see the distorted star fields and the bent light and the orbital velocities of stars that should not be moving that fast unless something massive and compact is holding them in orbit. The black holes themselves are hidden, sealed behind their event horizons, emitting no light, and yet their presence is undeniable. The universe betrays them at every turn. This brings us to one of the deepest questions in modern physics. What happens at the boundary where general relativity meets quantum mechanics? Black holes sit precisely at that boundary. They are macroscopic objects, large enough that general relativity describes them beautifully. The equations work. The predictions match observations. We can calculate the shape of space-time around a black hole, the orbits of nearby objects, the bending of light, the emission of gravitational waves, all of it confirmed. General relativity is extraordinarily successful at describing black holes from the outside. But at the center, at the singularity, the theory breaks down. The curvature becomes infinite. The equations give nonsense answers. And that breakdown is a sign that something is missing. General relativity does not include quantum mechanics, and at the scales where the singularity lives, quantum mechanics matters. This is the quest for quantum gravity, a theory that merges the smooth, continuous spacetime of general relativity with the discrete, probabilistic behavior of quantum mechanics. A theory that describes gravity at the smallest scales, where the fabric of spacetime itself might not be smooth, where distances and times might not be continuous variables but quantized into tiny discrete units. This theory does not exist yet, not in a complete tested form. We have candidates: string theory, loop quantum gravity, other approaches. But none of them have made predictions that can be tested with current technology. None of them have given us a clear picture of what happens inside a black hole, what replaces the singularity, what the structure of space-time looks like at the Planck scale, the unimaginably tiny length of about 10 to the negative 35 meters where quantum gravity effects are expected to dominate. Black holes are laboratories for this quest. They are the only places in the universe where the effects of quantum gravity might be strong enough to observe, at least in principle. The problem is that those effects are hidden behind the event horizon. We cannot see inside. We cannot send a probe to measure the interior. We cannot retrieve data from beyond the horizon. The black hole keeps its secrets. And yet, theoretical physicists have spent decades studying black holes because even if we cannot observe the interior directly, the properties of the exterior might give us clues. The temperature of Hawking radiation, if it exists, the entropy of the event horizon, the information paradox, the question of whether information that falls into a black hole is lost forever or somehow encoded in the outgoing radiation. These are windows into quantum gravity. Indirect windows, yes, but windows nonetheless. Stephen Hawking showed in the 1970s that black holes are not entirely black. Quantum effects near the event horizon should cause black holes to emit radiation, a faint glow of particles produced by the interplay between quantum mechanics and the curved spacetime around the horizon. The temperature of this Hawking radiation is inversely proportional to the mass of the black hole. For a solar mass black hole, the temperature is about 1/10,000,000th of a Kelvin, far colder than the cosmic microwave background. The black hole absorbs more energy from the universe than it radiates. For a supermassive black hole, the temperature is even lower. Hawking radiation if it is real, is extraordinarily weak. No one has ever detected it. But the theoretical prediction is important because it suggests that black holes are not eternal. Over unimaginably long timescales, longer than the current age of the universe by many orders of magnitude, a black hole will evaporate. It will radiate away its mass, it will shrink, and eventually, in a final burst of energy, it will disappear. This raises the information paradox. If a black hole evaporates, what happens to the information about everything that fell into it? Quantum mechanics says information cannot be destroyed. It can be scrambled, encoded, spread out, but it cannot vanish. If the black hole disappears completely, and if the Hawking radiation carries no information about what fell in, then information has been lost. The universe has forgotten. That violates quantum mechanics. But if the radiation does carry information, then the encoding must happen in a way that general relativity does not predict, because general relativity says the event horizon is a smooth boundary with no structure, no way to imprint information onto outgoing radiation. The paradox has been debated for nearly 50 years. It remains unresolved. It is a sign that our understanding of black holes is incomplete, that the smooth picture given by general relativity is missing something, that quantum mechanics has a role to play even at the event horizon. Some physicists believe the resolution involves the holographic principle, the idea that all the information about the interior of a black hole is encoded on the surface of the event horizon itself in a kind of two-dimensional projection. The interior might not be a separate region of spacetime with its own geometry. It might be an emergent description, a way of organizing the information stored on the horizon. This idea has gained traction in theoretical physics over the past few decades, particularly through work in string theory and the ADS-CFT correspondence, a mathematical framework that relates gravity in a curved spacetime to a quantum theory without gravity living on the boundary of that spacetime. The details are technical, the mathematics is dense, but the core idea is radical. Spacetime itself might be holographic. The three-dimensional universe we experience might be a projection of information encoded on a two-dimensional surface, and black holes are the clearest example of this principle at work. None of this is confirmed, it is all theoretical, but it shows how black holes force us to rethink the nature of reality. They are not just objects, they are puzzles. They sit at the intersection of the very large and the very small, the classical and the quantum, the known and the unknown. They are places where physics as we understand it breaks down, and that breakdown is not a failure, it is an opportunity. It is a signpost pointing toward a deeper theory, a more complete picture, a framework that can describe the universe at all scales, from the smallest quantum fluctuations to the largest structures in the cosmos. NASA has stated plainly that black holes are places where physics as we understand it breaks down. They are laboratories for extreme physics. They are testing grounds for theories, and they are important not just because they are exotic or dramatic or terrifying, though they are all of those things. They are important because they are real, they exist. They are out there, scattered throughout the universe, from stellar mass black holes formed in supernova explosions to supermassive black holes anchoring galaxies to the hypothetical primordial black holes that might have formed in the first moments after the Big Bang. They are part of the fabric of the cosmos, woven into the structure and evolution of everything around us. And their influence extends far beyond what we can see. The unseen influence. That is the phrase that captures what black holes are at the deepest level. They shape galaxies without being visible. They regulate star formation without emitting light. They anchor the cosmic web without occupying more than a tiny fraction of the space. They bend time and warp space, and erase the boundary between here and elsewhere in ways that general relativity predicts, but that no one fully understands. They hide singularities, or whatever replaces singularities, behind event horizons that seal off the interior from the rest of the universe. And they force us, every time we try to describe them, to confront the limits of our knowledge, the gaps in our theories, the places where the map of physics runs out and the unknown begins. We do not have all the answers. We are not close to having all the answers. Quantum gravity does not exist as a complete theory. The interior of a black hole remains speculation. The information paradox is unresolved. The formation of supermassive black holes in the early universe is not fully explained. The connection between black hole growth and galaxy evolution is understood in broad strokes but not in detail. There are mysteries everywhere, and that is not a failure. That is science. That is the process. You observe, you measure, you build models, you test predictions. And when the predictions break down, when the models fail, when the observations do not match the theory, you dig deeper, you refine, you expand, you search for the missing piece. Black holes are the missing piece, or more accurately, they are the place where the missing piece is most obvious. They are the clearest sign that general relativity is not the final word on gravity, that quantum mechanics is not the final word on matter and energy, that the two frameworks need to be merged into something larger. They are the reason physicists spend careers studying space-time, entropy, information, singularities, horizons, all the strange and beautiful structures that fall out of Einstein's equations and refuse to behave the way intuition says they should. And at the same time, black holes are ordinary. They are part of the galaxy. Sagittarius, a star, sits 26,000 light-years from Earth, quietly anchoring the Milky Way, occasionally flaring as a stray cloud of gas drifts too close, mostly just sitting there, patient, massive, invisible. It has been there longer than our species. It will be there long after we are gone. It is not malicious, it is not a threat. It is just a region of curved spacetime, doing what curved spacetime does, shaping the orbits of stars, holding the galaxy together, waiting. And if you could somehow stand on a planet orbiting a star near the galactic center, you would not feel its presence, you would not see it. You would see the stars around you moving in their orbits, some of them whipping past at incredible speeds, tracing ellipses that close in months or years. You would see the distorted sky, the bent light from more distant stars, the faint glow of the accretion disk if the black hole were feeding. But the black hole itself would be invisible, a hole in the sky, a patch of darkness where no stars shine. And if you did not know it was there, you might not notice it at all. That is the paradox. Black holes are the most extreme objects in the universe and the most invisible. They are the loudest when they collide, releasing more energy and gravitational waves than all the stars in the observable universe emit in light. They are the brightest when they feed, outshining galaxies. And they are the quietest when they sit dormant, hidden behind event horizons, silent, patient, waiting for the next meal. They are all of these things at once, and they are, above all else, real, not abstractions, not mathematical curiosities, real objects with real effects, shaping the real universe in ways that we are only beginning to understand. 4 million times the mass of the Sun. That is what sits at the center of our galaxy. That is the anchor, that is the engine, that is the unseen influence, the hidden architect, the wound in spacetime that has been there longer than the stars around it. And it is just one of billions. Every large galaxy has one. Some have more. The universe is full of black holes at every scale, in every stage of their evolution, and they are not going anywhere. They are permanent features of the cosmos, as fundamental as stars or planets or the space between galaxies. They are part of the story, and the story is not finished. The universe is still evolving. Galaxies are still colliding. Black holes are still growing, still merging, still shaping the structure of everything around them. And we are here, watching, measuring, trying to understand, building better telescopes, running bigger simulations, searching for gravitational waves, tracking stars near galactic centers, mapping the cosmic web, chasing the clues that black holes leave behind. The quest continues, the mysteries remain. And in the dark centers of galaxies, past the point of no return, beyond the reach of light, the black holes wait, silent, patient, inevitable, shaping the fabric of reality in ways we are only beginning to see. You stand on a planet orbiting a star you will never name, 26,000 light-years from the supermassive black hole anchoring the galaxy you call home. You cannot see it, you cannot feel it, but it is there, and it has been there longer than your species has had language, longer than your sun has burned, longer than the rocks beneath your feet have been solid. 4 million times the mass of the sun, compressed into a region smaller than the orbit of Mercury, sitting in the dark, patient, shaping everything around it without announcing its presence. And it is not alone. Every large galaxy in the observable universe contains one. Billions of them, scattered across billions of light-years, all of them pulling, bending, heating, regulating, sculpting the cosmos into the structure you see when you look up at night. Black holes are not monsters, they are not threats, they are not aberrations, they are architects. They built the universe you live in, not by design, not with intent, but by the simple fact of existing in a cosmos where gravity curves space and mass distorts time, and the rules, once set, play out without exception. They regulate star formation, they anchor galaxies, they drive jets that stretch for hundreds of thousands of light years. They shape the distribution of matter on the largest scales. And they do all of this while remaining, for the most part, invisible. We do not have all the answers. We do not know what sits at the center, what replaces the singularity, what happens to information that crosses the horizon. We do not know if white holes exist, if wormholes can be built, if the interior is a place at all, or just a projection of something deeper. But we know they are there, we know they matter, and we know that every question they force us to ask brings us closer to understanding the fabric of reality itself. The black holes are not the end of the story. They are the place where the next chapter begins.